So let's get recording on this. So as a basic setup, to make things simple, you can see it right at the very start of the chapter on page 820. Then your vector valued functions will either look like this, and we recognize that it's a vector valued function because we use vector notation. In the book, they use the bold text for the function r. Here I'm going to underline it to indicate it's a vector, but it'll indicate that it is a vector quantity. The input, however, t is a scalar quantity. That's just a number. Right, I'm underlining it, correct. If you were to put an arrow over the top, you can, but I've always underlined it, so that's my go-to. And so this will be, well, if it was a two-dimensional vector, then it will be some function of t as a coefficient of the unit vector I, plus some function of t times unit vector j. If it's in a plane, or if it's in space, then it'll be the exact same thing. But obviously, in this case, it's going to have a k component as well, which we'll call h of t. Okay. And so every time you've got a vector valued function, it turns a numerical input into a vector output. All right. So for example, r of t, to give sort of an excessively convoluted example, just to sort of illustrate the point, could be t squared plus e to the power ti plus sine tj plus the natural log of t plus 1 plus 3k. Now, it's hard to imagine any situation where that will be useful, but as a just generic sort of possibility, that will be a vector valued function. And notice that if I was, for example, wait a minute, let me go back and make this cosine of t. And so, for example, here, if I chose an input of 0, then my output would be 0 squared plus e to the power 0, so 1i, plus cosine of 0, so 1j, natural log of 1 plus 3, so 3k. Right, so there's an example of a vector value function turning a scalar input of 0 into a vector output of I plus j plus 3k. The vector that takes me from the origin to the point 113. All right, so that's the kind of thing we're going to be dealing with in this chapter. Right, that's the concept that we're introducing in section 1 and thinking about the graphics of it. Then we're going to move on and think about the calculus of these things as well and how we can use it. All right, but that's the basic idea. Now, bear in mind, let me switch back and give you a two-dimensional example, so I can kind of more easily draw some pictures to illustrate what I'm trying to say, rather than trying to draw three-dimensional vectors, which we've seen is a bit of a pointless exercise unless you've got some really good software. So let me erase that and instead consider R being, let's say, well, let's make it nice and simple in this case. Let's do ti plus t squared j. All right. So I could say that r of 0 here is just the 0 vector, doesn't go anywhere. And r of 1 is I plus j.
Is it possible to factor out the t?
Yes, but not really that worthwhile, to be honest. We don't tend to. I mean, it does obey algebraic rules, but you're more interested in having all the I component as its own expression, or the J, rather than. There are times when you might, but for the most part, probably no. R of 2 here will be 2I plus 4J, etc. Obviously, you could just keep on going with that. But let's think about what this means. Let me put R of negative 1 in. That is, R of negative 1 is minus I plus J. I'll plug in that value. So R of negative 1 would take me from the origin one space back, one space left and one space up. So there's R of negative 1 as a vector. R of 0, of course, doesn't go anywhere, so we'll kind of not worry too much about that. The 0 vector isn't a whole lot of useful, kind of physically useful property. It just needs to exist so that the math all hangs together, really. R of 1 would take me to the point 1, 1, because I go 1 unit right and 1 unit up. R of 2 would take me 2 units left and 4 units up. There. So here's my 1, 2. Excuse me. So different inputs give me different vectors, which as position vectors, i.e. starting from the origin and seeing where they go, lead me to different points. All right. But the thing that we're going to investigate is if I kept on going with that, if I generated, 10 different vectors here or whatever and considered them all, I would notice that in effect, a vector can be identified with a point, right? A vector isn't a point, a vector is a displacement, but when treated as a position vector, this vector here, 2I plus 4J, can be identified with the point 2, 4. So basically, just give me a second, actually. So basically, every vector that we've got, you can graphically identify with a point somewhere on the plane as well. And if we think about these points on the plane, if I was to sort of follow all of these, then I would find that all of these points wound up lying on a curve. Yeah, actually.
But it doesn't always have to start at the origin. 2I plus 4J could just be.
It doesn't, but we're choosing that we're going to make these, for application purposes, we're choosing, the word position vector means it starts at the origin. So if you describe something as a position vector, then you are saying it does start at the origin. And notice that all of those points lie on a parabola. And the reason they lie on a parabola is if we look back to our setup, in effect here, we're kind of looking at parametric equations, right? We've basically got x as a function of t, right? Our x coordinate is t, and our y coordinate is t squared. Now, back in pre-calc, that was parametric equations, which we also just did in the previous chapter as well. And I would say, well, the relationship there is that y equals x squared, right? Whatever x is, y is that thing squared, because that's the relationship that we're seeing. And so it's not surprising that all my points are lying on this parabola y equals x squared. So a vector valued function describes a curve in either in the plane if it's 2 dimensions or in space if it's in 3 dimensions, right? So in effect, a vector valued function is like a more compact version of parametric equations. That's the thing I want you to tie together between last chapter and this chapter is last chapter we were just doing parametric equations of mainly of a line, but in general you can turn that into a curve. This chapter is where you'll start to see it more as curves rather than lines. But I'm about to move this screen. Has anyone got a question on this screen before I move it off? So to try and sort of show you the big picture here, so before this, we have parametric equations. So x is some function of t, y is some function of t. Back in pre-calc, that's what parametric equations were. And you could be asked to graph them, what we call a plane curve, i.e. a curve in a plane. And back in pre-calc, that was typically an ellipse or a parabola or a straight line or a hyperbola or something like that. But it could be more than just conics. That was just what we stuck to in pre-calc. And in the previous section, we introduced the idea of 3 dimensions. I say, really, in the previous chapter, we only considered straight lines. In this chapter, we're going to move it into curves rather than just straight lines. But, you know, from a math point of view, just stick in one more equation in. Now, in vector valued functions, conceptually, we're basically dealing with the exact same thing, except it's now all rolled together. Rather than having 3 individual equations, we're just going to write that r of t is f of ti plus g of tj plus h of tk. But from a concept point of view, you're really dealing with the same idea. Now, I should point out, mathematically, these aren't the same things, because one is a vector and one is just a set of equations, right? Here, on the left side, I am just basically describing a series of points in the plane or in space that you would then join together to create a curve. On the right side, I'm describing a whole series of different vectors. But if you draw them all as position vectors, if you draw all of those vectors on one graph, the end of the vectors will be that exact same curve. Okay? So don't mix up the curve and the vector value function. They're not quite the same thing, right? The curve, so I got purple on this, right? The curve might be that. Now, because I've drawn that in 2 dimensions, there's no h to that, right? Because I'm just drawing it. If this was a 3-dimensional diagram, there would be an h as well. But the curve, that the parametric equations describe just the curve. All right. The vector valued function is describing this vector and this vector, and oops, that's not very good. Pretend the curve goes like that. And this vector and this vector, all the different vectors that take you from the origin to one of the points on that curve. All right. So make sure you're clear on the fact that there's 2 slightly different things going on, even though in your head they kind of belong together as a single idea. All right. But one thing is vector valued and one isn't. All right. The stuff that we talked about in the last chapter, we started off talking about vectors, but actually when it came to lines and surfaces and stuff, we didn't mention vectors at all. All right, now we're going to. Right, now our lines and curves are going to be done in a vector valued format. But that's kind of what it's showing you in the first couple of pages. And again, their diagrams are definitely better, especially when it comes to 3 dimensions. And so the first challenge that it really gives you is the idea of sketching the curve described by a vector valued function and reasoning through what it must look like using your knowledge of math and also using your knowledge of the things we just talked about in the previous section, because some of these curves will be embedded onto, say, an elliptic paraboloid or a hyperboloid of 1 sheet or something like that. The curve may be actually sort of inscribed on that surface. All right. Also, some other points to know, and right now I'm just kind of giving you a barrage of general info before we really get rolling. Right, the details are coming later. I'm just trying to give you a general overview where we're going. Also notice that a vector valued function will give you a curve. Right? It may be a piece of a curve because maybe t only takes on certain values. You know, you might be told over here, for example, that t only runs from A to B, for example. In which case, that might mean, that your curve starts here and finishes here, and you don't have anything else. So your curve may be just a piece of an overall curve with a start point and end point, or it may go on forever, right? Depending on whether you're given a range of values for t or not. But if you're given a vector valued function, then you are basically being given a curve as well, okay? But being given a curve does not uniquely determine the vector valued function. Yeah. You could, and you will see some, but they're a bit not early on just because they don't illustrate the basics as well. But yeah, you can. It's harder to imagine a reason for it, but it can. You could mathematically, absolutely, you could make one up. So let me try and give you an illustration of what I'm saying. Let's go back to that one I just did, where r of t was ti plus t squared j. Right? Which we said if I give you that, then it definitely means because the relationship there is that y is x squared, right? X is t, y is t squared, so y is x squared. So I'm definitely following that parabola, in the sense that all my vectors take me to points somewhere on this parabola, right? Also notice that just like parametric equations did back in pre-calc, there is a sense of direction to this curve, because as t increases, you're definitely moving, in this case, from left to right, as your value of t moves. Because, and I've said this once already, but it's the convention in math to use t as the input, but there's a good reason for it. You know, in applications, this is nearly always time. And so in that sense, time always increases from smaller values to larger values. Obviously, what we call the arrow of time in physics is very much one direction. And so if this is describing motion, if this is a particle moving, whether it's a particle moving under gravitational attraction or electromagnetic or some external force, there's going to be a sense in which it moves from one location to another as time passes. Right, so there's usually an arrow associated with these curves, just like there was back in pre-calc. But like I say, if I give you that vector valued function, you have to come back to me with that curve. It's the only thing there. But if I give you that curve, this isn't the only possible explanation or the only possible vector valued function generating it. For example, I could say, what about r equals t squared I plus t to the power 4j, right? That's the same relationship. Y is still x squared, right? Whatever value I pick for t, the x and the y value will have y equals x squared, right? Or what about if I said r of t is sine ti plus sine squared of tj? As long as y is x squared, then ultimately it's describing the exact same curve, right? So one curve does not have a unique vector valued function, right? You could basically all give me different correct answers to the question, give me a vector valued function describing this parabola, right? As long as all of you had the y term being the x term squared, you'd be good. All right. But there are slight discrepancies between exactly what's going on in those various things. For example, let's imagine you thought about this one. What about minus ti plus t squared j? Because that's still okay, right? I mean, that's still, y is still x squared. And negative t squared is still positive. Negative t times itself is still positive t squared. Why, though, is that not quite the diagram that I've drawn? Right? Because the arrow's pointing the wrong way for this one, right? In this one, as t gets bigger, x is getting more and more negative. Does that make sense? Everyone see that? This time, you know, over here, this vector originally was when t was negative 1. And this vector when t was positive 1, positive 2. So I'm definitely moving around this way. But on this one, this is t is negative 1, this is t is positive 1. This time I'm going this way around. All right. So with vector value functions, it's more than just the shape of the graph. There's more information contained in these things. The shape of the graph is a major part of what's contained, but the direction of motion is also embedded inside this. And things like, I don't want to go too far down this because this is a later chapter in what we're doing in this, a later section of this chapter, but the speed at which the thing is moving is also embedded in that. Basically, notice here, if t is 2, so imagine this is 2 seconds after the motion starts, takes me to 2i plus 4j right here. So in 2 seconds, I've got from this point to here. So there's some information about not only the path I've taken, not only the direction, but at what speed I'm going as well. Here, if I put t equal to 2, then I'd have 4i plus 16j. In other words, I've got all the way up to, you know, off the board, basically. So that's the same path, but 2 seconds there has gone much further. So it's going much faster. So, yeah, vector value functions are extremely useful in physics because they contain much more information than just what path something is traveling. They also tell you about direction and speed and acceleration, and therefore things associated with them like force, you know, physics applications as well. So this is quite subtle. You can miss the true value of vector value functions if all you focus on is the curve. But that was one of the benefits to parametric equations back in pre-calc, is parametric equations did exactly the same thing as your regular equations, except they stuck an arrow on there as well, which in pre-calc just seemed like a little wrinkle, basically, without a whole lot of value. Now we're really exploring the value of it. And the arrow is more than just which direction you go, like I say, it also contains information about speed, acceleration, and various things. So when it comes to modeling motion, there's a lot of things to bear in mind, and therefore a lot of things that you might need to think about in terms of what will be a helpful vector valued function. It's more than just finding anything that works for the path. You know, you're going to make sure that the direction works, the speed works, the acceleration works, and so on. So that's what this chapter is going to investigate. All right, but this section is really just introducing the idea. So let's think about another example. Can you think? Let's imagine I've got this set up. So let's imagine, because this can be quite frequently a useful piece of motion, something going around on the unit circle. right? Let's imagine I want it to go counterclockwise. All right. What's the equation of the unit circle? Well, that's my Pythagorean, but in terms of x and y for the actual equation of the circle, right, x squared plus y squared equals 1. And so I need x to be a function of t and y to be a function of t that satisfies that. So going back to the Pythagorean identity, what functions would satisfy that? Right, so one option would be to say then x is sine t and y is cosine t. Well, it could be either, right? As long as it's two functions that when you square each one and add them together, you get 1. So I could also have x equals cosine t and y equals sine t. Or I could have x equals negative cosine t and y equals sine t. No. Well, no, because if x was t, then y would not be given as a function, right? Because y will be plus or minus square root 1 minus t squared, and that will be a situation where you are needing piecewise functions, and if you don't need them, you wouldn't use them. So the fact that the trig functions dodge that bullet makes them much better. So think all of those pairings all satisfy the equation, right? Now, just think about the first two. X equals sine t, y equals cosine t. Or x equals cosine t, y equals sine t. And just like each of you, just before you answer, just think in your heads for a moment what the difference between them would be, and if one of them would work and the other one wouldn't on this diagram. Like I say, don't say anything yet. I just want you to think about if you can work that out. Ignore the third one for now. We'll come back to that.
In that arrow is supposed to be there?
Yeah.
Is the arrow like direction you wish to go?
Yeah, I'm trying to model this motion, so counterclockwise around the unit circle. So is there a reason to prefer one of those over the other?
Where do you want to start?
Right, now I haven't given you any indication of where I want to start. Right, and sometimes you may do. Sometimes the starting point might matter, other times it might not. Other times, it's just the motion going around the circle. But nevertheless, is there a reason to prefer one over the other?
Depending on where you want to start.
I just said it doesn't matter where you start.
In that case, probably the second one because it's the one we're most used to. Although an argument could be made to get us used to different concepts, so you could use the first one. It really just depends on what you're trying to accomplish.
No, there's more than that. You don't need to know that one of them works, one of them doesn't.
The first one goes counterclockwise. The second one goes clockwise.
Right? No, the other way around, right?
Oh.
If you think about the first one,
Yeah, because it starts at the top.
if t is 0, then x will be sine 0, nothing, and y will be cosine 0, 1. But then as t increases to pi over 2, x moves up to 1 and y goes down to 0, right? So basically, as t passes from 0 to pi over 2, you started here and gone to here. So this one's modeling clockwise motion. Whereas this one, when t is 0, x is 1 and y is nothing. Then when you reach pi over 2, you've got 0, 1. When t is pi, you've got negative 1, 0. So basically that second one is the one that's taking you counterclockwise. Do you see that? Is that making sense?
It's able to make x negative, if you want to make that one.
Right, yeah, so if you, I mean, I didn't write that one down, but if I wrote x to be negative sine t and y to be positive cosine t, yeah, that would be back to being counterclockwise. So this one doesn't work. What about the third one that I wrote down? Does that work or does that not work?
That would be clockwise, because it would start at 0. Then
Notice that a knowledge of unit circle information is crucial for this, right? You can't really do this question if you can't remember what cosine 0 is and sine of pi over 2, etc. So make sure you're all over that, because that's going to be all over these chapters, right? There's a lot of trig involved, and you'll need to know sine pi over 6, cosine 2 pi over 3, etc. So make sure you're on top of that. But the third one doesn't work, right? Third one also will give you clockwise motion. So out of those four, what seem like four possibilities, two of them don't work because they go the wrong direction. The other two do. So you could choose between r of t equals cosine ti plus sine tj, or negative sine ti plus cosine tj. Now, the difference between those two, like Ash says, is they effectively start at different places. If, as is often the case, if t equals 0 represents the start of your motion, the big difference between them is one of those starts at 1, 0, and the other one starts at 0, 1. Now, if that mattered, now you'd have a reason to choose between those two as well. But if all you care about is going around in a circle, then either one of those is good.
would it be possible to do more forms of that where you can just start at other points?
Yeah, I mean, there's basically any curve has an infinite number of vector value functions if you're prepared to look hard enough. But it's more a case of finding a good one, finding quote unquote the best one, which in this case you would say, well, this one just looks a bit better, right? I mean, it's got no negative sign in it. So why would we choose anything apart from that unless we had a reason to? What about, would this work?
No. No. That's not a unit circle then.
Is it not? Well, what about the rest of what you rest of you think? Does that work or not?
Yeah, it's just faster, right?
Right. I mean, x squared plus y squared is still 1, right? I mean, cosine squared 2t plus sine squared 2t still 1. But, yeah, it's going faster. Because now, by the t only needs to reach pi over 4 before you've gone from this point to this point. So whereas the first one here, as t goes from 0 to pi over 2, has made it quarter of the way around, this one's made it halfway around. You see that? So these two are describing the exact same curve in the exact same direction, but this one's going twice as fast. So it's very helpful when you can find ways to independently tweak the curve and the direction and the speed. If they're all tied together, it can be a harder job because you change one thing and you correct one problem, but you unfix an earlier problem or whatever. This is a good example because you can kind of basically mess around with all the things until you've got exactly what you want. If I wanted my circle to be radius 3, then there you go. Now my circle's radius 3. And we've already said if you wanted it to go clockwise, I would pick one of the other versions at the top. If I want to tweak the speed, I can just mess around with these coefficients of t here. So this is a good example of one where you can basically modify your function until you've got the exact radius you want, the exact speed you want, and the exact direction you want.
This also give you things like ovals?
Yeah. I mean, when we start, you know, if I made this 4 and this 3, now I'd have an ellipse instead of a circle, and so on. So, you know, later on, yeah, we'll be doing that. But for now, I'm just trying to get the basic idea for the concept. Now, as I said, it's generally a whole lot easier to work in 2 dimensions than it is in 3 dimensions, both in terms of working out what's going on and trying to sketch what's going on as well. But when you go through the book, you will see that they come up with some versions of that. So, for example, I'm just going to use the books one because I think it illustrates things well. So they give you one where x is 4 cosine, r rather, is 4 cosine ti plus 4 sine tj plus tk. So now you've got to try and fit 3 different things together. Well, the best thing to do really with this is usually to start by looking at the I and J bit, which, bear in mind, is in effect the trace, as we talked about in the last chapter. The trace is really like taking a shape and removing a dimension by flattening the thing down. All right, that's in effect what a trace is. So in this case, if I just looked at this, 4 cosine t plus 4 sine t, what's that? Circle radius 4, right? So in effect, what I'm dealing with here in the xy plane is a circle of radius 4. But of course, if I'm moving to 3 dimensions, then that becomes a cylinder, right? Give me a second, I'm finished. Right? This represents x squared plus y squared equals 4. But in 3 dimensions, that's not the equation of a circle, it's the equation of a cylinder. Because z is part of the paradigm, even though it doesn't feature in the equation. But I now know that r is a space vector going to 4 cosine ti plus 4 sine tj plus tk. In other words, as t increases, I'm going straight up. Right? The bigger t gets, the higher my value of z getting. So I'm basically moving on this cylinder, but I'm moving in such a way that I'm going around the circle and my z coordinates increase. So I'm basically spiraling up the cylinder. All right. So this represents a space curve, but this is how we're going to deal with space curves. Right? They're generally going to be curves that are inscribed on some surface. It's going to be the way that we can actually mentally think about them, because a space curve is just abstractly trying to look at 3 different things and visualize it straight away is not as straightforward as easy to graph as if, okay, well, what surface is being represented and what path on the surface is being represented. So notice in this case, when t is 0, then x will be 4, y will be 0, and z will be 0. I'll be starting at point 4, 0, 0. And then as t increases, I'll be moving clockwise around the circle, you know, clockwise in the xy plane, which in case, sorry, counterclockwise rather. In this case will be that direction, but also my z coordinates increasing. I'm basically spiraling up in this direction. Now, the curve itself doesn't need the green cylinder. The curve itself is just that. But both for drawing and also being clear what you're drawing, because if I just draw that, it's not very obvious exactly what's happening. That could be a plane crossing itself for all I know. So by drawing it onto a surface like the last time, it gives a bit more perspective, a bit more sort of a baseline to work from, if that makes sense. And so when you try, you want to try working around these surfaces as well. Okay, makes sense. So that's what they're kind of showing you. Example 1 is a plane curve. Example 2 is a space curve. The other thing that they do is sort of take that idea and actually define the curve as the intersection of two surfaces, because that's the other way you can do this. You actually had two surfaces that intersected somehow. And again, trying to draw this can be a real challenge, but let's give it a try. Let's imagine I have a cone, and then I had one of those parabolic cylinders, or an elliptic paraboloid, actually. Let's do that. So then basically there's going to be a curve that where these two things intersect, there's going to be a curve defined by those two that intersect. If you take two, again, I don't have all this diagram, I don't think is used to anybody. Their diagrams, page 822, for example, so much better. They've got an ellipsoid and a parabolic cylinder intersecting, and they're cheating and everything. Kind of shows you how the intersection is a curve in place. But the math of this, the good news is you don't really need to draw these things. You just be able to do the math, and that's a much simpler thing. So to give you an example, let's imagine I wanted the intersection of, let's say, I've got a hyperboloid of two sheets. Z squared minus x squared minus y squared equals 1. And let's start with a plane. X plus y minus z equals 0. So hopefully you can imagine if I take a hyperboloid of two sheets and I slice through it with a plane somehow, there's going to be a curve of intersection there. You know, whether that curve is an ellipse or a hyperbola or whatever, depends. Right, but it's going to create a curve of intersection, a space curve, and I would like to know a vector valued function to describe that space curve. Well, notice, in effect, I've kind of got a system of equations here, except I haven't got enough equations. I got 3 things I don't know, but only 2 equations. Notice that's okay, because all I really need is, I don't need to know x, y, and z numerically. In fact, that doesn't make any sense. That would be a point. What I need to know is how they depend on each other. In other words, I need to know the relationship of x and y and the relationship of x and z, or possibly y and z. So what I can do here is, okay, well, this thing here tells me that z is x plus y, which if I plug that up here, would say that x plus y squared minus x squared minus y squared is equal to 1. Well, if I expand that, oops, sorry, I've got my cross. Squared plus 2xy plus y squared minus x squared minus y squared is equal to 1. And so 6y is equal to 1. And so what I can say here is, for example, let x equal to, because I know x is going to have to be some function of t, so that seems to be the simplest one, right? I could pick anything. Why not pick x equals t? Well, if x is t, then what's y going to have to be? Right, so y must be 1, 2t. And then z, well, we know z is plus y. So z is going to be t plus 1 over 2t. So what's vector valued function? It's x. So ti plus y, 1 over 2t plus t, which is now t plus 1 over 2t. Okay. So the vector valued function that satisfies both of those requirements, right? If you check them out, if you're using these three expressions for x, y, z, z squared minus x squared minus y squared is 1, so that curve belongs on the hyperboloid of 2 sheet. Also, x plus y minus z is 0, so that also belongs on the plane. Therefore, it's the curve of intersection between the two. Now, that's not a unique answer. If you decided to make y equal to t, that would also be fine. If you chose to make x equal to t cubed, that would be fine. There is no answer to this question, but when you check in the back of the book, the thing you're most likely to see is x is t and y and z are whatever they need to be to make that work. So that has to be the convention, even though it's not the only option.
Would we be bound to this for like value t so it fits that intersection?
It depends what the curve is. I mean, a lot of curves aren't bounded; they go on forever. You usually see that in the domain of the function. So t can't be 0 here, but beyond that, t can be any positive value. So no, it wouldn't be bounded. And what you find in actual fact, this one, because of the way this is, t can't be 0, but it can be anything else. So this plane will be intersecting both pieces. T positive will be one curve here. T negative will be one curve down here. But right now, don't worry about that. Right now, let's focus on the map that produces that. So when you look at example 4 in the book, basically what's going on. So try those. So when you just read through the last 2 pages about limits and continuity, you understand limits in that one, then you understand limits here. It's basically just superimpose limits onto this idea, but you can read through it and get that. So I'll take questions next time, but the book does a perfectly adequate job of explaining limits and continuity without me needing to go through it really. So in terms of homework, going through question, at least through question 38. Some of the later questions are also, they give you more practice, but I think, going through question 38 will give you practice on the basics of what you need to know for this. So try those, and try and have your test graded by tomorrow. Is that all right? Questions? All right, guys. See you tomorrow. Are you okay there? Any questions on that?
Question about number 26. Yeah, I was having a tough time trying to figure that one out.
26.
Yes.
So RT is t squared plus ti and t squared minus tj. Okay, let me get this up. So this is 12.1. 26. So a plane curve. So we're basically working with this parametric equation of t squared plus t for x and t squared minus t for y. So, I mean, you can sometimes sort of see straight away relationships or finesse stuff, and other times you kind of pretty much have to just sort of brute force this thing. So notice that if I was to add these together, x plus y would be 2t squared. Oops. Right. And if I was to subtract them, then x minus y would be 2t. Right. And so, in effect, kind of my relationship here is if I square both sides of this, x minus y squared will be 4t squared. But 4t squared is twice 2t squared, so it's 2 times x plus y. So basically, that's the direct relationship between x and y. In terms of actually sketching the thing, I don't know if they're intending you to just use a graphing utility to do that. Well, I'd have to complete the square on y to do that, because if I expand, if I try that, so I've got x squared minus 2xy plus y squared equals 2x plus 2y, which means that y squared minus 2y minus 2xy is 2x minus x squared. I mean, I think I've got a feeling this is the folium of Descartes, the shape, but I can't think of a time at which you would have ever been actually officially told about a shape like this. In fact, this is very much one of the shapes that you would deal with parametrically, rather than trying to find the direct relationship between x and y. So, short of just generating a load of points, picking a load of different values of t and generating a load of points and join them together, I'm not really sure how it's expecting you to do this. Because I mean, this is a perfectly valid equation. I mean, it's not it doesn't define y as a function of x. It's not uniquely defined. But that's the equation of the curve. But it's not any kind of curve that we commonly use. You know, it's not one that you can write y as a function of x in any meaningful way. So it's not something, you know, it's not like a parabola or something that you're familiar with. So to be honest, I'm not really sure what it's expecting there. It's even numbered, so I guess it doesn't give the solution in the back either. I mean, you could put that into your calculator parametrically and see what it looks like. But off the top of my head, I don't know what it looks like.
Would this be the kind of question that you would ask us on the test? Like graph it? I mean,
no, no, because a knowledge of arcane geometric shapes is not really what I'm testing here. I'm interested in, do you understand the idea behind interpreting the vector value function? So, you know, you'll still be using very much the kind of basic shapes that we've been using. I said, I mean, if you've got a graph calculator, you can do it, but I'm not even sure why that is helpful particularly either. So that's probably why you're struggling with it, Christian, because there's only so far you can get with that.
Yeah.
Because all the other ones in there are quite easy to actually produce the graph. but not that one. That's not a well-known expression. Okay, so I left you at the end of yesterday just to read through the idea of continuity and limits, basically because it's exactly what it's always been. I mean, there's just nothing new. When we write, you know, in Calc 1, when we talk about limits and continuity, you know, we'll be talking about some function f of x, and whether the limit exists, whether the function's continuous at a point. Bear in mind, for the limit to exist, then the limit from the left and the right must both be defined and be equal. And for the function to be continuous, the limit must exist, the function must exist, and they must be the same thing, right? Those are two things established right back at the start of Calc 1 that we used to then create the definition of the derivative and start working with that. So, you know, we'll talk about the limit as x approaches c of f of x, and we'll talk about f of x being continuous at x equals c, which basically implies that the limit as x approaches c from the left of the function equals the limit as x approaches c from the right. I don't know what happened there. C from the right of the function, which will therefore be the limit, and that will be the function evaluated at c, right? Well, so that was Calc 1. In Calc 3 now, when we've got r of t equals f of t I plus g of tj, which we may stop there, or we may have a space curve with h of tk. When we talk about limits and continuity, we're basically just saying that's true for all three of those functions. If we say that this vector valued function is continuous at t equals 6, then we're basically saying f, g, and h all continuous at t equals 6. So it's not a new idea, it's just now embedded into at least 2 and possibly 3 times the word, yeah. But conceptually, it's the exact same thing, which is why I just left you to read through it. And in establishing the derivative, it's also going to be the exact same thing. So we're kind of going to breeze through in about 5 minutes what in Calc 1 we took several days to do, because we would just be repeating those days. And you can't be in this class without having understood pretty comprehensively what was happening in Calc 1 first time around. So I entirely trust that you will be happy with it second time around. And so that's what section 12.2 takes and runs with. It introduces the definition of the derivative. And so bear in mind, you know, that again, let's do it's frequently useful in Calc 3 to compare what you're doing with the equivalent from, well, so far last chapter it wasn't Calc 1, it was pre-Calc. Everything we did last chapter had an equivalent in pre-Calc, whether it was parametric equations or conic sections or whatever, but we never got as far as calculus. This section will have a lot of parallels with the start of Calc 1. But in Calc 1, we defined f prime of x to be the limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x, or something similar, right? The notation sometimes varies from book to book. You know, you could use h instead of delta x, and there is an alternative way of writing it, but that's your base definition of the derivative, right? And you can't do that, of course, without an understanding of limits, which is why limits are the first thing that you do, like the last thing you do in pre-calc and the first thing you do in Calc 1, because you have to be able to evaluate limits to deal with that. Well, in Calc 3, same again, just triple the work, basically, where if we want to define r prime of t, and you see this on page 828, well, it's basically the limit as delta t goes to 0, because it's a function of t, not x, of r of t plus delta t minus r of t divided by delta t. This, of course, will be a vector valued function, because the expression involves vector valued function, which is hardly surprising. All right. If the limit exists. If the limit exists, we say that the function is differentiable. If the limit doesn't exist, then the function is not differentiable. Some functions are not differentiable at certain points, but for the most part, ones we're interested in. But the reason I kind of don't dwell on this, the book goes into it in more detail. It kind of actually proves it. But basically, as we said before, r of t, let's keep going with the 3D version, because the 2D version is always just the slightly simpler form. As you might expect, the derivative here, r prime, is just the derivative of f as a coefficient to I, derivative of g as your coefficient to j, and if necessary, h prime of t. Okay, so all you're really doing, same again as what Ashley said, is really 3 times the work. You've got 3 different functions embedded into one, and so 3 different derivatives to find, but you just find them one at a time. It's basically like 3 Cat 1 questions in one, or possibly 2 if you're only dealing with planar motion. And as you can well imagine, higher order derivatives are the same. If you want a second derivative, well, f double prime I plus g double prime and so on. So, although it's a new concept, it's, from a math point of view, nothing new at all, which is why it's not really worth spending much time on. Yeah, Ash.
What happens if we want to take like the second derivative of r prime of t, and we want to take the second derivative of r of t, but like f of t doesn't have a second derivative?
Then r of t doesn't have a second derivative either. All 3 have to exist for it to, yeah. One of them is enough to take down the rest. But then,
so would it be like a 0? Or like
the thing is, there aren't many functions for which a derivative just blanket doesn't exist. I mean, there may be a function whose derivative doesn't exist at a point, but that's meaningful in calculus, right? It meant that there was a non-differentiable point, i.e. maybe like a cusp or something. For example, just get rid of this. If we were dealing with this function, for example, we'd say that that's not differentiable at 0. But that doesn't mean that the function somehow disappears at 0. It means that the graph has a sharp turn in it, which is actually a very important characteristic of the graph and tells us something. So similar, we may well find that some of these functions are not differentiable at a point, and that's going to tell us something about the surface when we, or the, sorry, not the surface, this is a vector value function, so a curve when we get there. So yes and no, it doesn't mean that you can't do anything, but if one of them, the derivative doesn't exist at a point, we'd say that function isn't differentiable, so we would say that r itself is not differentiable as well at that point, even if only one of them was the case. And so section 2 is basically differentiating and then later integrating vector value functions, but yeah, it's really just more of Cat 1, all the same functions, same rules, same everything. There's no new rules, there's no new functions that are suddenly going to pop up. We're still talking about polynomials, trig functions, logarithms, exponentials, your standard functions to integrate or differentiate. So I'm just going to give you a bit of practice, but having said that, although the calculus is exactly the same, there's going to be certain properties that emerge that will tell us something useful and that we can make use of. But the calculus rules haven't changed. So I'm going to give you r of t, and that's going to be sine 3t I plus t squared j minus 3 cosine, sorry, try that again, cosine 3t rather. Okay. Now, just before I go any further, can you think about what that might look like?
Circle, but with a spiral in the y direction.
Yeah, spiral in the y direction, exactly right. Basically, this one x squared plus z squared is 1. So this time it's a circle in the xz plane.
And is the spiral also spelled?
Right, and unlike the one, so circle in the xz plane. So my cylinder's going. No, let's try that. I've completely messed that up. It should be going along the y-axis. Rid of all of that, so I'm not paying attention. So cylinder, circle in the xz plane, so like that. But unlike the spiral that we had yesterday, which was kind of basically moving sort of regularly straight up, this spiral is going to be progressively stretching out because it's t squared rather than just t. And so, no, it'll still be a spiral, but it's almost like you're like taking a slinky, but one end of it is broken, almost like it's been distorted. So it'll kind of start off like this and then stretch out and stretch out. So from the side,
So like the space between them will get larger.
right? From the, oh, that shouldn't be getting wider. This should be all, but yeah, the space between will be getting wider. So that's basically the curve being described. But this time I'm not really interested in that so much as the derivatives. So see if you can work out r prime of t, r double prime of t. I'm not going to do all of the things I've got written down here just because it may be too time consuming. R prime dot r double prime. I'm going to stop writing t, although all of these things depend on t. And we'll start with those three. I'm going to put one more down and decide what the best one to do is.
One of my question was, what if it didn't exist? What if, for example, like r of t was just sine 3ti plus tj? So like it would be t and then it would be 1 for the first prime, for the second prime.
Oh, zero, yeah. So it doesn't, I mean, it doesn't not exist, it's just zero.
Okay.
But that will, you know, in fact, we'll be talking about what that means as we start interpreting this. Right now, we're just doing the calculus rather than actually getting a meaning out of it, but we will do.
k for for something that's supposed to be a number to have a variable in it?
What do you mean?
Because whenever you do dot product, you're supposed to get a scalar constant.
Well, a function of t would be a scalar.
In respect to t.
Right, I mean, it just means it's not vector value. Well, t here is a scalar. So if your dot product was something like 2t plus 5,
T was a variable, not a scalar.
those two aren't mutually exclusive.
Oh, but
Scalar is something that has only magnitude, not direction.
I know scalar was a constant.
No, it's a numerical value. So a variable is a scalar too. As long as it's not vector value, then it's scalar. So what's our prime of t here?
3 cosine 3t plus 2tj plus 3 sine of 3t.
And remember this, it's entirely up to you which notation you use, either the IJK or that notation. I'll try and switch between them just to remind you how they're both there, because the book uses both. So I want to keep you kind of reminded of how those notations work. What about our double prime?
Minus 9 sine 3t I hat plus 2j hat plus 9 cosine 3t.
Right, so there's our prime and our double prime. Now later in the chapter, we're going to primarily be sort of focusing on what that means, what we can actually do with these derivatives, what physical applications they have. But right now, we're just practicing differentiation and then later integration rules. But notice, if I do r prime dot r double prime, right, because I'm going to get minus 27 sine 3t cosine 3t plus 4t plus 27 sine 3t cosine 3t.
Does it normally work out that way, or is it just...
When circles are involved, sometimes yes. We again, that result will make a bit more, not a bit more sense, but you'll see more of a value to that one again when we start talking about r prime and r double prime as given physical interpretation. But for right now, that's just one of those things. So the answer there is just 40. I threw the other two on at the end, the cross products of r and r prime and r double prime. So let's just go to the next page and do that. So r cross r prime, IJK. So r, remember, was sine 3t, t squared, and minus cosine 3t. R prime, therefore, was 3 cosine 3t, 2t, and 3 sine 3t. So if I do my cross product, well, the I component, I will get 3t squared sine 3t minus negative, so plus 2t cosine 3t. The j component will be 3 sine squared 3t plus 3 cosine squared 3t, which is what? If I do the j component, I'm going to get 3 sine squared 3t plus 3 cosine squared 3t. Just 3, right? Because sine squared 3t plus cosine squared 3t is just going to be 1. Negative 3, of course, because it's the j component.
Oh wait, wouldn't it be positive because there's a minus?
No, because remember it's this minus this. So it's 3 sine squared 3t minus negative, so plus 3 cosine squared 3t. That's 3, but then j always needs a negative sign in front of it.
Wait, j always? Yeah. Oh, because it's the way you do it.
Yeah. It's just a rule. It's not the way I do it. It's the way it has to be done. That'll make more sense when you get to matrix determinants in linear algebra, then you'll see why. That's for now just.
I did it different. I think I was thinking the way your method works mine.
What other method is there?
You take that ijk sine 3t t squared. You take that, you just double it on the other side, and then you do that. Where you go cross, 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 and then cross the other way.
Okay. If you're confident that gives you the right answer, then by all means. Did you get -3? Okay, well, that's fair enough.
Do you normally take linear algebra after calculus?
Either afterwards or at the same time, depending on which semester. Because we offer Calc 3 every semester, but linear algebra, well, certainly used to only offer every other semester. So you can take them co-rec, or you can take linear algebra after Calc 3. It doesn't really matter. This is the only time there's any kind of impact, if you like. And you know, you don't need to know about determinants to apply this rule. So. Oh, really? I mean, there's really no reason why. It's just kind of the setup. But it's usually some linear algebra. I guess I think I can't remember if it's co-rec with this or if you just need Calc 2. Maybe you just need Calc 2. I never teach it, so it's not. I don't really tend to think about the pre-rec, co-rec requirements. The k, that will be 2t sine 3t minus 3t squared. Oops. Minus 3t squared cosine 3t. So that's r cross r prime. This right now is really just more practice of cross products, but this time using functions of t rather than just numbers. So we're, like I said, we're getting not numerical answers. You know, my answer is a vector, but it's a vector that depends on t. But it is worth just comparing these two. If I do r cross r double prime, I will get I, j, k, sine 3t, t squared, and negative cosine 3t. And this time, the next one's going to be minus 9 sine 3t, 2, and 9 cosine 3t. Right? That's my r double prime. So if I do my cross product here, notice the I will be 9 t squared cosine 3t plus 2 cosine 3t. The j will be 9 sine 3t cosine 3t minus 9 sine 3t cosine 3t. So the j component will be 0. And the k component will be 2 sine 3t plus 9t squared sine 3t. The reason I've put those there is that now it's not immediately obvious, but actually if you differentiate r cross r prime, the first one with respect to t, let's think about what we get. I'm going to need to use the product rule on these. So I get 6t sine 3t plus 9t squared cosine 3t plus 2 cosine 3t minus 6t sine 3t. Well, notice the plus 6t sine 3t and the minus 6t sine 3t cancel, and what's left is this. So actually, if I differentiate this, I get this. And of course, if I differentiate a constant, I get 0, and then the same thing here. So actually, the derivative of the first one is the second one, which is why we kind of went through that process. And the reason why that's not just a coincidence here, that's always going to be the case, because basically, as we talked about, when you talk about vectors, there is no multiplication. You can't multiply vectors. So there's no product rule per se, because there's no such thing as a product. But there is a dot product and a cross product, which sort of function very much like multiplication, and they have their own version of the product rule. So let's just kind of remind ourselves of the product rule. Going back to Cat 1. If I'm differentiating UV with respect to X, what do I get?
Plus V prime U.
Right. That's the product rule, right? Back in Cat 1, when we're just doing ordinary functions, not vector valued functions. Well, basically the same rule holds true if you're either doing dot product or cross product. So the derivative, for example, of, let's say, R1 dot R2 will be R1 prime dot R2 plus R1 dot R2 prime. So if you understand the product rule, then you're really not going to be particularly surprised by the version of it that applies to vector valued functions. And if that was a cross product, it would be exactly the same. If this had been R1 cross R2, then it would have been R1 prime cross R2 plus R1 cross R2 prime. And so notice in this case, if I apply the product rule here to R cross R prime, I will get R prime cross R prime plus R cross R double prime. Right? That's the product rule here. But if you remember what we said when we define cross product, any vector cross with itself is 0. And so it's not surprising that all that was left was R cross R double prime, because the first bit was a guaranteed 0. So for any vector, the derivative of R cross R double prime, sorry, the derivative of R cross R prime will be R cross R double prime. And you see all those properties on page 830. It lists how the derivative works, but predominantly number 4 and number 5. Yes, yeah. Number 4 and number 5 are the new equivalent of the product rule. There's no quotient rule equivalent because there's absolutely nothing even close to dividing as far as vectors are concerned. But the dot and the cross product are close enough for multiplication that you get a parallel there as well. All right. And so the book takes you through some examples of showing you those properties. They are very much just work through, crunch the numbers examples. There's nothing much, there's no new concepts being introduced. It's a lot of examples of, it's a huge mix of differentiating functions, doing dot products, doing cross products. It's just all mixed together in big questions. The last few minutes I want to spend talking about integration, because as you might expect, that works very much the same as well. But we have to bear in mind the difference of differentiating and integrating. One is a lot more specific than the other. So let's imagine that R of t again is f of t I plus g of t j plus h of t k. I think the easiest thing here is to actually use an example. So R of t, I'm going to make, say, 10 over 4 plus t squared I, plus e to the negative 2tj. And I'm just, giving you practice here, basically, plus secant squared tk. Let's imagine I wanted the antiderivative of this. Instead of differentiating, I want to integrate thing. Now, worry about definite integrals later. Let's start with indefinite integrals, say we do calculus. So in effect, I just need to, this has now become 3 separate questions from Calc 1 integration rather than Calc 1 differentiating. But I'm really asking you to find antiderivatives of 3 different functions. I don't have to write it like this. This may be overkill, but just derive from you what we're actually doing here. So what is, do I integrate 10 over 4 plus t squared? Find people's memory of integrals are as good as their memory of derivatives, but it is. One question. Anyone go a little further and tell specifically? Obviously, tech's got nothing to do with it. Combination.
It's a squared plus a. I know it right.
X over A, and don't forget the coefficient of 1 over A outside as well. So that would be, you'd be 10 times 1/2 inverse tangent of X over. Right. Inverse tangent and inverse secant, you get a 1 over A factor. Sine don't. Again, these are all just details. You know, they're all here in the book if you look for memory. Or actually, all on the inside cover. You know, this every rule inside was all the differentiation, the integration rules. By this point in the book, you know, there's nothing that we have reached at that point. This will be 5 the tangent of t divided by t. What? Is that what do, but before to that, plus you're right. The thing is, you know, when I'm differentiating, I get a unique answer. When I'm finding antiderivatives, I get a family of answers, right? So plus C. How did you know what C was in Calc 1?
Well, we're plugging this into our t, so that's expected to give a value we can't do variables.
I mean, in Calc 1, if I asked you to find antiderivative, you'd just leave a plus C, right? Unless I gave you some extra information. But normally, you just have a plus C there as part of your answer. But of course, when we move on, what's the antiderivative of e to the negative 2t?
Negative 1/2 e to the negative 2t plus c.
Right. Now, you do have to be careful here because in math, you know, once you've ascribed, you know, a piece of notation, then it's fixed. So actually, I can't just write plus c again because I would be implying that this plus c and this plus c were the same thing. So this one, yeah, is going to be, I'll go back and call that C1. This one can be C2. What's the antiderivative of secant squared t? Tangent t plus C3. Okay. Now, frequently, we don't really want to have these 3 different constants hanging around, messing things up. So often what we'll do is actually separate, in effect, distribute the ijk and regroup. So instead I could write this as 5 inverse tangent of t over 2i or minus 1/2 e to the negative 2tj plus tangent tk, and then separately write c1i plus c2j plus c3k. But of course, this thing here is just a constant vector, right? This isn't like 3i minus 5j plus k. So actually, it's easier to just write plus c as a vector. You actually backtrack, and in the end, actually, you do only need plus c. Basically, you can just integrate the 3 or 2 maybe, or 3 different functions as is, and then stick a plus c on the end, but now that c is a vector, not a scalar. So plus c needs to be acknowledged as a vector. In the book, it'll be in the bold type. You know, if you want to stick an arrow over it or underline it or whatever. But, you know, you have 2 options. You can either write plus c1 plus c2 plus c3 for the ijk, so you're listing the components, or you can write plus c as a vector to indicate this is just any constant vector will do, right? Either one of those is fine, but you'll see one of those happening in the book when they do it. And basically, having said that, again, there's nothing else in the book beyond just recapping integration methods and integration facts from before. So although we haven't spent much time on 12.2, really you should now be able to just read through it and do the problems, because there's no new material, it's just a new context. The only thing that is new, and for now I'll just say read it, and I'll remind you of it at the start of Thursday. There is a definition at the top of page 830 about describing something as being smooth, a curve being smooth on an interval, and that is new. It's very simple. It just means that the derivative r prime is not 0. But that's something that you haven't seen before. So remind me Thursday. I will recap that and do an example of smooth. But everything else in the homework should be just, in effect, review material set into a vector context. All right. So try those and ask me about them Thursday's class. Thursday we'll get going on some more useful stuff where we start interpreting these things physically. Any questions? Alina, you okay? You got any updates on return? Let me get recording. So as we said yesterday, projectile motion, basically any motion where an object is given an initial velocity, and then from that point on, its motion is determined only by gravity. So we'll have some initial displacement of a height h, where the object is, and then some initial speed at some initial angle. And because we're going to deal with everything in terms of horizontal and vertical, everything's going to be I and j in terms of when we do the vector value function, I really need to know what the components of this initial speed are. So let's just think about what we've got here. I've got this initial vector v0, although v0 we're actually going to denote as a scalar quantity just to be the speed. The length of the arrow obviously represents the magnitude, the speed. The direction I'm really reflecting in terms of this angle theta. And so if I picture a right triangle here, where in effect these are my two components of the velocity, vertical component and horizontal component. Let's call them A and B in terms of size. Well, sine theta here, of course, is A divided by V0, opposite divided by hypotenuse. So A, the length of the vertical side, is V0 sine A. Sine theta, rather. And similarly, cosine theta is B divided by V0. And so B, the length of the horizontal component, is V0 cosine theta. In other words, this initial velocity V0, is V0 cosine theta I plus V0 sine theta j. All right, that's my initial velocity expressed as a vector in terms of the speed and the angle. Because for most things, the speed and the angle are the more practically useful things. When something begins motion, you won't know its individual horizontal and vertical components. I mean, if you were told that V0 was 3i plus 2j, great. That would be very useful in terms of doing the math. It would make your life a bit easier, to be honest. And it's possible that might happen in a question. But the reality is, you know, if someone hits a baseball, you can't look at that and determine the horizontal and vertical components. What you can determine, you know, in terms of what you're going to get told the stats on, you're going to be told the angle and the speed. Right? Those are the things that can be more instantly measured, and so they're the more convenient values to give. So if we think about what we've got here, well, we know that the acceleration is simply negative gj, right? Because the acceleration of the object is the Earth's gravitational field acting on it straight down with a strength of 9.8 meters per second squared or whatever, but what we're going to denote just as g. All right, negative because it's going down, whereas j goes up. Which means that my velocity will be the antiderivative of that with respect to t. Well, now I should have said yesterday, notice, you know, we did say yesterday this motion will be entirely in a vertical plane. So I'm free to point the x-axis whichever way I want. So I don't need 3 dimensions here. I can just point the x-axis in the direction of motion. So y-axis will be straight up, basically measuring the height of the object, and the x-axis will be in the direction of motion, measuring the sort of horizontal distance traveled. So I don't need a k, right? This is entirely a 2-dimensional analysis. So I and j I'll pick appropriately to keep the motion inside the plane. So when I integrate, there's no I component, so that'll become C1I. Integrate my 0 to get a constant. And when I integrate my J component, well, negative G is a constant, so that'll integrate to negative GT plus another constant I'll call C2. But I know what V is when T is 0, right? V of 0 is C1I plus C2J when I plug in T equals 0. And I know now that that's V0 cosine theta I plus V0 sine theta J. And so C1 is V0 cosine theta, and C2 is V0 sine theta. So that initial piece of information tells me the value of the two constants. Again, don't forget, in any given question, you will be told V0 as a number and theta as a number. So these are constant values. V0 cosine theta, there's no variable to that. That's just going to be fixed by the initial speed and the initial angle of inclination. So that means that V at any given time is V0 cosine theta I plus V0, V0 sine theta minus GT J, which notice means that the velocity of the, and again, I'm just going to keep this as a baseball just for illustration's sake. This can apply to anything really moving through the air. But if we think about it as a baseball, the velocity of the baseball, the horizontal component is just fixed, right? It's just traveling on a horizontal level without speeding up or slowing down because there's nothing to that, right? Newton's laws say that an object either continues at rest or in a state of uniform motion unless acted on by a force. Well, horizontally, there is no force. So there's nothing to speed it up and nothing to slow it down. So it's just stayed, whatever the initial horizontal component of velocity was, that's what it sticks on doing. The vertical component, though, is getting reduced as time passes. As t gets bigger, minus gt is slowing down the vertical component, and it will eventually turn it negative. In other words, the object will stop going up and eventually start coming down, which all is exactly what you would expect. And then if integrate again to get the position, well, this time if I integrate the I component, V0 cosine theta is a constant, and so that'll integrate to V0 cosine theta t plus something. And in the J terms, well, V0 sine theta again is a constant, t. T integrates to t squared over 2, so this will be minus 1/2 gt squared plus some constant. Right? So that's my second time finding an antiderivative. But again, I also know what the initial position vector is, right? The initial position vector, well, when I plug t in here, I've got C3I plus C4J. But my initial position vector is just HJ. Right? It started on the y-axis, so 0I. I haven't done left or right, but I have gone h units up, so that HJ. And so C3 is 0, and C4 is H. And so finally, here's my position vector at any time for this projectile. It's V0 cosine theta Ti plus, let's write it, so H plus v0 sine theta t minus 1/2 gt squared j. So that's the vector that starts at 0h, has the initial velocity that we were given, and has an acceleration vector of negative g. And so that's the position vector. But let's think about what that means in terms of the path, right? I mean, basically here I've got parametric equations of x equals v0 cosine theta t and y equals h plus v0 sine theta t minus 1/2 gt squared, right? That's parametrically what I'm looking at. So sort of thinking back to pre-calc where we did parametric equations and how you can work out the curve. Well, the method was always to eliminate t. So t is x divided by v0 cosine theta. So I'm going to plug that into my second equation. So I'm going to rewrite that y, but instead of t, I'm going to write x divided by v0 cosine theta. Again, don't put off, v0 cosine theta is a constant. You know, t is like x divided by 2 or something like that. Right? There's a lot of different letters there, but not many of them are, only x and y are only x, y, and t are variables. Right? v0 and theta and g are all fixed values. All right. So if I plug that in, y is h plus v0 sine theta t, which is now x divided by v0 cosine theta, minus 1/2 gt squared, which is x squared over v0 squared cosine squared theta. In other words, y is h. Here the v0's cancelled, so I've got x tangent theta minus g over 2 v0 squared cosine squared theta x squared. And again, this looks, don't get thrown here, this looks a bit of a mess, but tan theta and h and this whole g over 2 v0 squared cosine squared theta, they're all just numbers. So for example, in one situation, this could be y equals 3 plus 2x minus 5x squared. Right, that's the kind of thing I'm looking at. It will always be a quadratic function of x, and the coefficient of x squared will always be negative. Because notice what I've got minus g, which is always 9.8 or 32, depending on which units you're in. G's a positive number. And then v0 squared cosine squared theta, that's got to be positive as well. So they're squared. So the coefficient of x squared has to be a negative number. So what shape of graph does that represent? A parabola, right? And a downwards opening parabola, because it's always got a minus something x squared. So basically what you're looking at here is a parabola, and notice that the y-intercept, if you put x equals 0, the y-intercept is h, as it should be. And so if you graph it, well, you change the different values of theta and v0 and stuff, you'll change exactly what parabola we're looking at, but we're basically looking at something like this. Except practically speaking, of course, the motion starts here. So what I'll see is this, and then obviously at some point the ball's going to hit the ground, at which point the motion stops. So you know, from a math point of view, the entire parabola goes on forever, but I'm only really interested in the part of it that physically means anything, the bit where the ball's in the air. But projectile motion is always parabolic, right? Any object traveling through the air under gravitational force, or gravitational attraction rather, follows a parabola. Now, as I said yesterday, we have idealized this slightly. We're ignoring air resistance. We're ignoring any lateral, you know, pressure imbalance or anything. So, you know, the reality is if you actually track a baseball that's hit, it's not a perfect parabola, but it's very close. And so, you know, that allows you to work out, for example, you know, if you know where you're hitting from, you know how far it is to the boundary, you know what distance is required for a home run, you know what height you've got to clear the boundary, you can work out, you know, what speed is needed and what angle is needed. You can kind of optimize roughly what you're hitting. As you might expect, an angle of 45 degrees is going to do the best. Anything greater than 45 degrees, you're kind of wasting time going up and then coming down. At less than 45 degrees, you don't get as far before you hit the ground. So if you want to optimize the distance traveled, 45 degrees would do it. But close to 45 degrees is kind of what you're looking for. All right. So that's projectile motion in general. So let's look at an example. Well, any questions on that before I clear this? I'm happy with it. Clear this. So we'll have a ball is thrown from the top of a 100-foot cliff. At 30 feet per second at an angle of 60 degrees to the horizontal. And the two questions we're going to look for are, what's the maximum height of the ball? i.e., what height does it reach before it starts to fall again? And what's the total distance traveled? How far away from the cliff will it be when it finally lands? Whether it's landing on land or water, I haven't really said. Let's say water. So we've got our cliff, and water down here. So the ball's being thrown here at 60 degrees to the horizontal. 30 feet per second, so I know it's going to take some parabolic trajectory. And so the question basically wants to know, well, firstly, what's this? What's the maximum height that it attains in this path? And secondly, what's this? Well, let's plug in what we know here. And I can kind of use my result that I just got rather than doing all the integration again. So don't forget R of t is V0 cosine theta t. Well, V0 is, oh, let me write that in. So 30 cosine 60 degrees t I. And then I've got h. What's h here? 100. Plus V0 sine theta, so 30 sine 60 degrees t. Minus 1/2 gt squared. What's g going to be in this particular case? No, in this case, right. Basically, 9.8 will be if my units were meters. I should pop it in there. Yeah, 32. Since this is setting up units of feet for distance, and I want 32 feet per second squared. So minus 1/2 g will be 16 t squared j. Well, I can go a bit further than that, right? What's cosine 60? 1/2. So this is going to be 15 ti. And then 100 sine 60. It's over 2. So this is going to be 15 root 2 t minus 16 t squared j. So this is what I meant when I was saying don't get put off by all the symbols in the general formula. This winds up just being, you know, fairly straightforward quadratic. I know the square root 2 is there, but beyond that, that's not too bad. So that's r of t. Now let's think about the question term. Firstly, the maximum height. Well, what do I know is the situation when this thing reaches its maximum height? Which one? Velocity, right? The the vertical component of velocity will be 0, right? It's always going horizontally at the same speed, but it's been going up, then it's going to come down. So for a moment, there's going to be a 0 vertical velocity. So actually for that, I need v, not r. So if I differentiate, I'm kind of going back to where I originally came from here. This will be 15i, which kind of backs up what we said. Horizontal component's just always 15. This thing horizontally is always traveling 15 feet per second. But in terms of the vertical component, the 100 disappears. I'll get 15 root 2 minus 32t. Which, if you remember originally, it was v0 sine theta minus gt. So there's the minus gt you can see there. So maximum height occurs when 15 square root 2 minus 32t is 0, which tells me the time when that happens. So the value of t will be 32 divided by 15 root 2. Now, to do a problem like this properly, you are going to need a calculator. You know, I could leave this in terms of square root 2s and stuff, but if you talk applications, you really want, you know, decimals. You want numerically useful values. So this will be 1.51 seconds. Now, that's not the answer, of course. The question is, what's the maximum height? So how am I going to do that? Right, plug it back into R, specifically the J component, right? Because I only want to know the height. So the answer to, there you go, actually, yeah, thank you. So the answer to part 1 that I asked would be 100 plus 15 root 2 times t, which is 1.51, minus 16 t squared, so 1.51 squared. So that's going to be hang on, that's not, I've written down something wrong here, that's not working out. Maybe I've either written something down or I'm typing it in my calculator wrong, so that's not working out. I think that calculator, I think I use this phone calculator is not allowing it in. Let me just check I haven't made a mistake on screen though before I write that off. Oh, okay, yeah. This should be 15 root 3, right? Not 15 root 2. That's what's written wrong. It's square root 3 over 2. So these should all have been square root 3s, not square root 2s. That's why. So that 1.51 is wrong. Should have been. Well, I'm not going crazy. So it should be 1.23 seconds. Sorry, not 1.51. And with that, hopefully this will work. Root 3 as well. So 107.7 feet. So basically it didn't go much higher than it was before it maxed out and then started to drop again. Basically because 30 feet per second is not that much when it's countering gravity. So it got another 7.7 feet up and then started dropping again. All right. So that's the answer to the first bit. I'm going to leave the second bit for you to try at home, but how will you find it? What situation creates a situation where I'm looking at maximum range? Which part of position is 0? The J component, right? The I component is what the question's asking me for, but I know that the J component will be 0 when it hits the ground. So basically I go back to this. Put that equal to 0 and solve it. Now, of course, that'll give me 2 values, but I only want one of them. Why will the other one not make much sense? Because it'll be negative, right? And that makes no sense for T, right? Ball can't land before it was hit. So although I'll get 2 values, I only care about the positive one. I'll take that and I'll plug it in here to get me the answer. But I want to leave enough time to move on. We need to make a start on section 4 here if we're going to get it finished on Monday. So I'll let you finish that at home. But that's a fairly standard kind of question you'll see in the book about projectile motion, finding maximum range, maximum height, time when it, you know, I could have said, what time does it land? Which you'd do the same thing, it's just, you know, now you just solve the quadratic equation, you wouldn't have to plug the answer in. So you'll see a variety of those questions in the homework problems. But I want to get on to section 4 because this is where it gets particularly useful in terms of physics application. See, so far, and in that problem that we just did, we've been splitting our motion up into horizontal and vertical components, right? Which can be very useful if it's projectile motion because all the force is in a vertical plane, right? The force is applied vertically, there's nothing horizontally. And so by split it up into horizontal and vertical components, we can kind of consider them one at a time, each with their own particular sort of set of applied force or whatever. But there's plenty of other times in nature and physics, in motion, where we're not really interested in horizontal and vertical forces so much as what we would call tangent and normal directions for force. Because let's say an object is moving on a path like this, for example. The idea of considering the horizontal and vertical components of force, right? I mean, let me let me redraw this slightly. If my object is here, the idea of horizontal and vertical components of force, so this would presumably be subject to a vertical force down because it's moving down towards the x-axis, and a horizontal force right because I'm assuming, I didn't draw an arrow on, but I'm assuming it's kind of going left or right here. But the reality is those two forces are not, or those two kind of analysis of the forces isn't really what I'm looking at, because for the most part, forces generally either cause objects to move forward or they cause them to turn, one of the two. And forces that, if a force is in the direction that you're moving, it causes you to either speed up or slow down. But to move forward, you basically need something that is projecting you in that direction. And to turn, you need a force left or right, because as I said, Newton's laws of motion, objects continue in a straight line unless they're acted on by a force. So really, that's not, it would work, but it's not really the most useful way of doing this. What would be much more useful is if I took, for example, a point over here in the motion, if I analyze the forces that were, the force component in the direction that the object is moving at that time, and then also at 90 degrees to that, which in this case I would expect to be in that direction because the object is turning in that direction, right? If you've got a sideways force, a lateral force, then that's going to make you turn one way or the other. So rather than split my analysis into horizontal and vertical like we did with projectile motion, where it made sense, here I'd be much better splitting all my forces into one component running parallel or running tangent to the curve, and another component running normal to the curve at 90 degrees. And so instead of having an I component, J component, remember those are two unit vectors, I and J. Here, we're going to split it up into two different unit vectors, and the symbols we give these, this one we call the unit tangent vector, and this one we call the unit normal vector. But notice it's a function of t, because at different points, the tangent and normal vectors will point in different directions, right? The unit tangent vector will change as you move around the curve, and so will the unit normal vector. All right, and so this section is analyzing how you actually work out what these two things actually are, because previously our force and therefore our acceleration, might have been, something. I guess I'll use let's use P and Q or something. So it might have been PI plus QJ, right? Might have a horizontal component, a vertical component. Now instead, we're going to take our acceleration vector and make it some component in the tangent vector direction and some component in the normal component direction. But again, it's going to be more complicated here because unlike I and J, those things change as time passes. All right. And so we're going to spend some time analyzing how you determine those things. And it's going to turn out that it's not too bad in 2 dimensions, but it gets quite complicated in 3 dimensions. Because pretty much the only thing we're working on here is that they're both unit vectors. So they both have a magnitude of 1, and they are normal to each other or orthogonal. So the one thing I know is that t dot n needs to equal 0. Otherwise, they wouldn't be what I'm saying that they are. They are always at 90 degrees to each other. All right, so that's the requirement. Now, the unit tangent vector is a pretty easy thing to work out what it needs to be, because as we've already said, You know, if we've got a path, it's because we've got r of t, right? A vector valued function gives us a path, as well as a direction of motion and a speed and an acceleration, etc. But we've also said how the derivative r prime, which of course is velocity, but it's more than just velocity, it's really a geometric property of the curve, always points tangent. Right? We said this last time, is that, you know, if this is r prime, you know, how long it is depends, but r prime will always be tangent to the curve, right? By definition. So the unit tangent vector is a unit vector parallel to r prime. And if you think back to pre-calculus, how do you make unit vectors? You take the vector and you divide by its own magnitude. So that gives us a formula for the unit tangent vector. Right. Which you will see on page 845. So working out the unit tangent vectors, nice and straightforward. If you're given r for your motion, or you work out r depending on the situation, then you can work out r prime and you can divide by its own magnitude. Again, that since r is a function of t, so is r prime, so is magnitude r prime. So this whole thing will be a function of t. What about the unit normal vector? Well, I need to create something that definitely has a magnitude of 1 and definitely is 90 degrees to the unit tangent vector, always. Well, what do we know? What will I get if I do the unit tangent vector dotted with itself? It'll be 1, right? Or, well, it'll be, it's, you know, any vector dotted with itself has its own magnitude squared, and the magnitude is 1 here. So, because remember, it'll be magnitude t times magnitude t times the cosine of the angle between them, which of course is 0 because it's the same vector. But it's a unit vector, so magnitude is 1, cosine 0 is 1, so the whole thing is 1. Let's differentiate that with respect to time. What was our product rule here? It was t dot t prime plus t prime dot t, and that'd be equal to 0 because obviously 1 is a constant. So 2t dot t prime is 0, which basically tells us that t prime must be pointed in the direction of it, because I know that t and t prime will always be orthogonal because their dot product is definitely 0. So this is giving me the direction of n. The only thing is, it needs to be a unit vector, so t prime isn't quite good enough. I need to divide by its magnitude. And so there's the definition or formula, if you like, for the normal vector, which you will see on bottom of page 846. But that doesn't look much, but there's a lot of problems. That's a much more confusing thing than it looks. Because notice that t at the top, t will be a function of t divided by another function of t. What was that question? Isn't that just the double direction of that magnitude? I don't know what you mean. No, that's not the double. No, it isn't. Because the derivative of t, r prime, the magnitude of r prime isn't constant. So to do t prime, you'll need the quotient rule. Right? Top's a vector, bottom's just a scalar, but they're both functions of t. And so you'll need the quotient rule. The quotient rule. And then you'll be divided by magnitude. So that's what I mean when I say that looks a lot simpler than it often ends up being. So actually, we're not going to work out n that way. Although that's the definition, the way we'll work out n will be dependent on whether this is 2 dimensions or 3 dimensions. So 2 dimensions is actually pretty easy. 3 dimensions quite a bit harder. So I want to at least get to the 2-dimensional version today so that Monday we can focus in on the space curve idea in 3D. So if we're sticking in 2 dimensions, which is basically what I've just drawn, some curve. And again, let's say we're at this point here. Well, unit tangent vector is pointing in this direction. Unit normal vector is pointing in this direction. So as we said, t will be r prime divided by r, magnitude of r prime. That won't be too bad to work out. That'll wind up being some function of ti plus some function of tj. I mean, we're still going to have to write our vectors in terms of I and j. We want to think about the components that are tangential and normal to the motion, but we're still going to have to express them as vectors. Well, n needs to be a vector whose dot product with t will definitely be 0. Well, the way to guarantee that is to switch the 2 coefficients around and make one of them negative. Right? If I make n y of ti, well, I can't make it. I'm going to write something down wrong now, plus x of tj. If I think about the dot product there, the dot product will be xy plus another xy, which is not what I want. That's not 0. But if one of them is negative, then it's going to be xy minus xy, which is a definite negative. Notice, though, I don't know which one to make negative. So I either make that one negative, or I make the first one negative. Which kind of makes sense, right? Because basically when I draw in my my unit tangent vector, there's actually 2 different options for the normal vector, right? Technically, they're both normal vectors, and those are the 2 things I've written down at the bottom. One of them points one way, one of them points the exact opposite because it's multiplied by -1. But in any given situation, I want to choose the one which is kind of concave, if you like, the one in which the curve is turning. I'll basically do that by simply looking at the graph and deciding, right? Just abstracting it down to the math without thinking about the graph and the curve will mean that you don't really have a good way of making that decision. But as soon as you look at it, you will. And again, notice it's not even the case that I can say which one it's supposed to be, because for some values of t, it will be 1, and for some values of t, it'll be the other, right? If I was to pick this point over here, there's my tangent vector, and there's my normal vector. So notice at the red point, the normal vector points to the right for the motion, but by the time I've got round to the green bit, now the normal vector is pointing to the left because I've gone through a point of inflection, basically. So it's not even the case that I can generally say whether it's this one or this one. Sometimes it'll be the first, sometimes it'll be the second. You basically have to make that decision looking at the graph and looking at which point on the graph we're specifically interested in. But if we had, for example, let's pick a nice easy one since I've only got a couple of minutes left. We'll do the more complicated stuff on Monday. Let's imagine that r of t is 2t squared plus 1i plus 3tj, which you could work out what shape that curve was if you wanted. So r prime will be 4ti plus 3j, which means that the magnitude of r prime will be the square root of 16t squared plus 9. All right? Happy with that? And so my unit tangent vector is 4ti plus 3j, all divided by that expression. You know, if you want to write it in the vector form, then it's 4t over the square root of 16t squared plus 9, 3 over square root 16t squared plus 9. But notice, trying to do t prime here is not straightforward. You've got two components, and each one will need both the quotient rule and the chain rule. It's going to be quite messy. You can do it, but it's going to be quite messy, especially when all I need to say is that n here will be whatever I get when I switch those two components and make one of them negative. So it's either going to be 3 over square root 16t squared plus 9 minus 4t over square root 16t squared plus 9. Or the negative version of that. So let me just stick a plus or minus sign outside. But notice if I do t dot n here, multiply the I components, I'll get 12t over 16t squared plus 9. Multiply the j components, I'll get negative 12t over same thing. So when I add them, guaranteed 0. So in 2 dimensions, actually n is very easy. Take your answer to t, switch them around, and make one of them negative. Or I should say change the sign on them, because one of them may already be negative. Change it back to positive. But switch them around and change the sign on one of them. Now again, the only thing that's an issue here is that right now, this is undetermined. And it's not the case that I can tell you how to work out which one to choose. There'll be different places where you choose the positive and the negative on the curve, depending. So you'd have to graph the curve to work it out. But I'll show you examples of that on Monday. You know, in terms of just the base work for determining t and n in 2 dimensions, that's what you're looking at. Does that make sense? You happy with that? You know, if you want to sit down and do t prime divided by magnitude t prime, you will see that you get the same result, and you will see how long it takes you to do it, and I don't think you'll ever want to do it again. All right, but you would at least, you know, verify that it does actually work out. But when we move into space curves on Monday, where there's I, J, and K, this method is too simplistic. It's not going to work. We're going to have to do something cleverer to work out the normal vector, which I'll go through with you on Monday. But for now, any of the plane curve questions in section 4, you should be able to do. Don't do any of the space curve questions until later. So if K is involved, leave it. If just I and J are involved, you can do it right now.
All right.
Okay. Enjoy your weekend, and we'll finish this on Monday. Thanks, Asha. Recording. So if you're given a plane curve, you know, r of t equals something I plus something j, then unit tangent vector will be r prime divided by the magnitude of r prime. by definition. And that will be some function of ti plus some function of tj. And then in the plane, we know that the unit normal vector will simply be the vector you get when you switch those coefficients and change the sign on one of them. So either plus or minus yi minus xj. Because that's the only way to guarantee that the dot product of t and n will be 0 as it needs to be. Right. But if we move up to a space curve in 3 dimensions, that method for n isn't going to work anymore. Right, so let me give you an example where we'll start it, then take a break, and then come back to it. Here we go. So I've got this example. Plug this in before I forget. So I've got r of t, vector valued function is t squared I minus 2t squared j plus t cubed k. Before we go any further, let's try and think a little bit about what this curve would look like. Well, let's think about the xy plane here. X is t squared and y is negative 2t squared. In other words, y is negative 2x. So on the xy plane, we're simply following this line. Y equals negative 2x. That, of course, is actually a plane coming out the board or coming out the screen. And the entire motion will take place in that plane. Right, when t is 0, of course, I'll be at the origin. And then as t increases, I'll be going in that direction. But also as t increases, notice z is increasing because z is t cubed. So basically I'm moving along that line, but I'm coming out of the board and z is increasing at a faster rate than x and y, because it's increasing as t cubed instead of t squared and negative 2t squared. So basically I'm kind of curving out the board, becoming steeper and steeper. So basically this curve is coming on this plane, but it's coming out on a curve. So it's I mean, in some sense, it is still a plane curve, but it's not in the xy plane. And so I can't make use of that, short of trying to do a very elaborate change of coordinates, which we haven't talked about. I have to treat this as a space curve, even though it does exist in its own plane, but not the xy plane, not the xz plane or anything like that. So that's what the curve is going to look like. And I want to know the unit tangent vector and the unit normal vector at any position on that curve. All right. Notice if you allow t to be negative, t negative actually would take me back towards the origin, right? Because this bit of the plane, this bit of the line won't ever exist because x is t squared, so x is always positive. And y is negative 2t squared, so y is always negative. So actually, if t is negative, you come along this line to the origin, then turn around and go back again. But not z. If z is negative, actually, so if t is negative, then z is negative. So basically, it starts off inside the board, kind of sweeps along that plane up to the origin, and then comes out again and sweeps away from the board. So there'd be kind of a sharp turn at the origin if you were to map the entire graph. I won't try and draw it because I don't think it would make a whole lot of sense. And frankly, the process for doing this doesn't require you to be able to picture the thing at all. I'm just trying to link that together with what we've already talked about. So, in terms of what we would actually do, I'll leave it green actually. So R prime. So I missed out the I earlier, so I should go back and put that R prime will be 2ti minus 4tj plus 3t squared k, which means that the magnitude of R prime will be the square root of 2t all squared, so 4t squared, plus negative 4t squared, so plus 16t squared, plus 9t to the power 4. You all right there, Christian?
What? No, it's fine. I'm getting this.
No, I was sending you to sleep, but it's okay.
What? No.
I have that
you
effect.
weren't.
I have that effect on people. So the 4t squared and the 16t squared, obviously I can add to give 20, and I can factor t squared out of the whole expression, which can come out of the square root of just a t. So this will be 20 plus 9t squared when I simplify that down. And so when I come to work out my unit tangent vector, notice I'm actually going to have a factor of t top and bottom, because it's going to be r prime, so 2ti minus 4tj plus 3t squared k, all divided by t square root 20 plus 9t squared. And so this t will cancel the t factor there. And so I've got 2i minus 4j plus 3tk all over the square root of 20 plus 9t squared. Yes, that's correct, Ashley. So that's my unit tangent vector. Now, so we could, for the unit normal vector, follow our formula. Notice I can't make use of the same idea as I did last time, because when you're talking about a space vector, it's not the case that there's only one possibility, or I guess technically two possibilities for an orthogonal vector. With a space curve, the only way you can absolutely guarantee a vector to be orthogonal, i.e. the dot product to be 0, is to switch the coefficients and change the sign on 1. But here there's plenty of ways I could pick another vector that's orthogonal to that. But which one would be the normal vector, I wouldn't know. Right? The issue being, let me see if I can kind of do it on a graph. I'll come back. So here's my unit tangent vector. Is everyone happy with this? Right, I'll be returning to that later. But let me try and illustrate, visually what I'm talking about. If we have a two-dimensional curve, as we were talking about last time, at some point you've got your unit tangent vector. Now the direction's kind of visually obvious because it's the tangent line, and the length of it has to be 1 because it's a unit vector. And there's only two vectors normal to the curve there, in other words, orthogonal to that. One of them is this, one of them is this. So you're picking one of those two, right? It's either N1 or it's N2. You pick the one that the curve is kind of turning in the direction of. So in this particular case here, N1 will be what I call my unit normal vector. Not N2, because that's the curve's turning the other way. Okay? But if we move into 3D, this is where we'll see if I can get something that is meaningful or not. If I've got some curve, then at a point, I can find my unit tangent vector visually easily enough, but there's lots and lots of vectors now orthogonal to that. Basically making up a plane, right? If you think back to what we did in the previous chapter, the unit tangent vector is like the normal vector to the plane. And any vector in that plane would count as normal, right? It's like I've got a whole slice going across here that's perpendicular to t, and any vector in that plane is orthogonal to t. So instead of having 2 possibilities for n, I've got an infinite number of possibilities for n. Any vector in that plane is a candidate for being a normal vector. But obviously most of them aren't. You know, only one of them is actually in the plane of both the curve itself and that blue plane that I've drawn. So it's not a case here of it being easy to just look at your value of t and switch stuff around to decide which vector will be orthogonal to it, because instead of 2 options, and when I say n1 and n2 aren't really 2 options, they're really just 1 option, and then you choose which direction it goes. Because don't forget up here, n1 is simply negative n2. So they're not really 2 options. It's just 1, and then you decide which direction it's supposed to point. Whereas over here, you've got nothing really. That's not a viable way forward. So we're gonna, I'm not gonna say we're gonna scrap that because we never had anything to scrap, but in 3D, that's not an option. So what next? Well, don't forget the original idea for n was that it was t prime divided by the magnitude of t prime. Now, that's not impossible, but it becomes really, really messy and complicated to simplify afterwards, right? Let's just go back to what I had for t before, having written it down. It was 2i minus 4j plus 3tk over the square root of 20 plus 9t squared. So t prime is going to need the quotient rule on each term. Then you're going to have to find the magnitude of that whole thing, each of which will be quite complicated. Then you've got to take t prime and divide by its own magnitude, and then you've got to simplify the whole thing, right? Now, believe it or not, this one actually wouldn't be quite as bad because 2 of those 3 coefficients are constants, but it would still be a mess. If every one of your I, J, K components depended on t, it would rapidly get horrendous. So we basically don't do that. We kind of we approach the problem completely backwards from what we originally intended to do. The whole point of t and n, if you remember what I said, was that let's imagine we've got a curve, and temporarily I'm going back to 2 dimensions just because I'll be able to draw it better. But let's imagine we've got some curve and I've got some point. What I'd really like to do is take the forces acting on the point, acting on whatever the object is at that point, and resolve them into 2 directions, but not horizontal and vertical anymore. What I'd really like to do is know how much force is tangential to the motion and how much force is normal to the motion. Basically because tangential force is what generally controls the speed of an object. I mean, it controls the acceleration, and by doing so controls whether it's speeding up, slowing down, whatever. Whereas the normal force generally controls whether an object is turning or not, and to what extent it's turning. Whereas if you split it into horizontal and vertical, then the net horizontal force isn't contributing one particular characteristic to this, nor is the net vertical force. Whereas the tangential and normal components of the force, and therefore acceleration, are having 2 distinct effects, right? If you're driving a car and you're turning, the force that's sending you forward, the force that's basically keeping you driving, that's counteracting the friction resistance of the road, is being generated by your engine. Whereas the force that's causing you to turn, because you only turn with a force, right? If there's no force, you carry on going in a straight line. The force that's causing you to turn is being generated by the reaction of the road on your tires, the friction reaction force, which is going to be in a normal direction to the direction of motion. Right. So you've got two completely different things providing the forces, and you want to be able to treat them as two completely different concepts to do the work. So I want to take my acceleration, and I don't want to split it into something I plus something j. I instead want to split it into something in the t direction plus something in the n direction. And those somethings we call the tangential and normal components of acceleration. So the reason we're studying t and n at all is because in physics, it's a very useful thing to decompose acceleration into two orthogonal components. One tangential to the motion, one normal to the motion. But again, don't forget, t and n themselves depend on t, right? The tangent vector where I've drawn it, if I was interested in this point over here, then there's two different, t and n are two different, in fact, sorry, n would be this direction over here. So, what, the tangent vector isn't something fixed. It changes as t changes, as you can see at the top, right? This t that I've written at the top of the screen is a function of small t. It'll have a different value depending on whereabouts you are. So what we're going to do is actually work backwards. You'll see on page 850, it gives you the formula for the components of acceleration. And it also shows you why. For time purposes, I'm going to let you just read through why it is. It's a fairly easy proof. But so when we write A equals A sub tt plus A sub n, A sub t, the tangential component of acceleration, involves a dot product. It's v dot a divided by the magnitude of v. Which, don't forget, is the same thing as saying r prime dot r double prime divided by the magnitude of r prime. Because v is velocity, it's the first derivative of r. A is acceleration, second derivative of r. An, the normal component of acceleration, is the same idea, but it's the cross product. There are other formulas you'll notice when you look in the book, but these are the two ones that basically give you directly from R the results. All the rest, to some extent, this one, it's also useful. The other formula that they give you is A dot t, dot product of AT, which you can see that because A is R double prime and T is R prime divided by its magnitude. So, basically they're saying exactly the same thing. One's just substituted the formula for unit tangent vector. An is A dot n as well, but the problem is we don't know n. In fact, we're going to use this to find n. So although this is an expression for acceleration in terms of its tangential and normal components, what we practically use this for is to find everything except n and solve for it. So this is going to basically give us an equation to solve to find n, and I'm going to show you in terms of the example we just did what that would look like. Now, it's still plenty of work. It doesn't come easily. But it is at least a piece-by-piece process. You're not trying to do any one massive thing in any one step. So let's go back to my example that we just did. And I'm going to clear the screen because I'll need the whole screen for this. So, but I guess let's work out the things that we know. So so let's just go right back to the start. So R was t squared. I'll go back to the other. Try and make it a lot more compact here. The other notation, that was R prime was 2t negative 4t and 3t squared, which means that R double prime will be 2 negative 4 and 6t. Right, so which of course is also my acceleration as well. So we've already said that t is 2 negative 4 3t all divided by the square root of 20 plus 9t squared.
Isn't it the 2t?
It's r prime, so it was this one, but then there was a t. Remember the?
Oh, right,
so
right.
I've cancelled this t with all the t's running through.
Of course, yeah.
And so a sub t is v dot a divided by magnitude v, or you can just treat it as a dot t up here. So it'll be r double prime, which is 2 negative 4 6t dot t, which is 2 negative 4 3t divided by square root 20 plus 9t squared. And notice, of course, that is going to be, when I do the dot product, it'll be 4 plus 16, so 20, plus 18t squared, and divided by the square root of 20 plus 9t squared. Okay. Happy with that? So I know A, because the question gives me R, which it quickly allows me to get R prime, R double prime. So I know A, V, and R. So I know A. I now know A sub t, because I just worked it out. I know the unit tangent vector, because I've written it over here, I've worked that out. I've still got to work out the A sub n, the normal component of acceleration, and then I'll know everything in that expression except for n itself, the normal vector. So let's quickly work out A sub n. A sub n, well, before I do that, I need to know what V cross A is. In other words, R prime cross R double prime. Well, that'll be IJK. R prime, remember, is 2t negative 4t and 3t squared. And R double prime is 2 negative 4 and 6t. So the I component will be minus 24t squared plus 12t squared. So minus 12t squared. The J component will be 12t squared minus 6t squared. So 6t squared, but I need to stick a negative sign in because it's J. And the K component will be minus 8t plus 8t. So 0. All right. So actually notice I can factor negative 6t squared out of this, and it's 210. And so A sub n, which is the magnitude of this, divided by the magnitude of V, which was my t square root 9t squared plus 20 or 20 plus 9t squared, whichever way you want to write it. Well, the magnitude of that, negative 6t squared is just, that is a magnitude, that's 6t squared. And the magnitude of the vector will be the square root of 4 plus 1 plus 0. So this is 6t squared times square root 5 all over t root 20 plus 9t squared. And finally, that one of those t's cancels. So there's my a sub n. So everything's a function of t here, right across the board. But that will be the normal component of acceleration at any given time. Now, there's plenty of applications where that's all you care about. You only care about the size of the tangential and normal components of acceleration rather than specifically the direction, in which case that's all you need. But if I need the normal unit vector, or the unit normal vector rather, then I'm going to construct it from here. So we're going to go back to this idea. And sub in everything except for n and solve for it. So let's do that. Now, like I say, you see, this is not a quick process by any means, but I'll let you, if you can either take my word for it or you can check for yourself at home that doing it the other way is just as bad, but at least this way you break there's lots of smaller steps, and each step by itself is just kind of one thing to do. So you don't run quite as much of a risk of the whole thing just collapsing around you. But it is entirely up to you the way you want to do it. If you prefer the formula for n, then you're welcome to use that. So let's put in what we know. So my acceleration vector, which is 2i, I'm going to put it in the more compact way just to fit it all on the screen. So 2i, negative 4j, and 6tk is equal to a sub t, which was 20 plus 18t squared over the square root of 20 plus 9t squared, times my unit tangent vector, which was 2 negative 4 3t divided by the square root of 20 plus 9t squared, plus a sub n, which we just did, is 6t square root 5 all over square root 20 plus 9t squared times n. And n's the thing that I want. So I'm going to call n, I'm going to call it n1i plus n2j. Oh, that's not, I'm not, I bet I need to keep the same notation there. So let's just write it as so n1, n2, n3, because I don't know any of those. Now, I don't have to do this, but hopefully you can kind of see enough to see that it's going to help. I'm going to put that over square root. I'm going to build a square root 20 plus 9t squared into the mix. Simply because I can see that every other term on the right has that. So I'm kind of expecting it to be there, right? So if the unit tangent vector had that denominator, I wouldn't be surprised if the unit normal vector did as well. And it's going to make my simplification a whole lot easier, because now when I multiply these things together, you know, these terms are getting multiplied together, so those two square roots will just become the single denominator. And when I multiply these two together, same thing will happen. So I didn't have to put that there. If I just called it n1, n2, n3, then when I finally worked out what they were, they'd all feature that denominator themselves. But by building it in right from the start, I'm going to make life a whole lot simpler for me. So if you see the same denominator running, which you always will, running through all the terms, just build that into the way you write n right from the start. Because notice that now I can multiply through by that expression. Multiply left side and right side by 20 plus 9t squared. Right? And now I am going to write it out in terms of the ijk components. So if I do that, I'll have 20 plus 9t squared times 2i minus 4j plus 6tk And on the right side, well, my denominators are gone, so I've got 20 plus 18t squared times 2i minus 4j plus 3tk plus 6t square root 5 times n1i plus n2j plus n3k. But what I've now got is a vector on the left equals two vectors added together on the right. But as we've talked about before, for two vectors to be equal, then their I components need to be equal, and their j and their k. So let's think about the I components, right? I compare the coefficients of I. On the left side, I've got 20 plus 9t squared times 2. And on the right side, I've got 20 plus 18t squared times 2 plus 6t square root 5n1. So there's an equation in n1. The only thing I don't know there is n1. T, of course, is part of the answer. So if I think about this, if I multiply out, I've got 40 plus 18t squared equals 40 plus 36t squared plus 6t square root 5n1. Well, 40, I can subtract 40 from both sides. And I could subtract 36t squared from both sides. And so n1 is minus 18t squared divided by 6t square root 5, or minus 3t divided by square root 5. Right? So by comparing all the I terms separately, I create an equation where the only thing I don't know is n1, and I can work it out. See if you can work out n2 and n3 the same way. So with the J components, the same thing. Distribute. This time, if I add 80 to both sides, I'll cancel and add 72t squared to both sides. So I will get 36t squared equal to 6t square root 5 n2. And so n2 will end up being 6t divided by square root 5. That's what you get from n2. The k components. I'm sorry, I just back and just that happen. Hope just the connection is good enough. The k components are got 20 plus 9t squared times 6t. 20 plus 18t squared times 3t plus 6t square root 5 and 3, which if I distribute will be 120t plus 54t cubed equals 60t plus 54t cubed plus 6t square root 5 n3, and this time the t cubed terms cancel. Subtract 60t from both sides. And so this time when I divide, the t's cancel, the 60 and the 6 cancel, so I just get a constant value of 10 divided by square root 5, which I'm not going to rationalize because they've all got square root 5 denominators. Right? And so that's what you should get for n3. All right. Which basically means when I put all that together, I can create my normal vector n. So is there any questions on that before I do? Yeah, Alex. Right, you mean in the red? Here?
Not the green. Like where it's 20
This?
plus 9t squared 60 per 10.
Here? Oh, from here.
Oh.
I'm comparing the k coefficient, so it's this times 6t is the coefficient. Okay. And so when I put all that together, oh, sorry, Olivia.
I didn't figure it out.
Okay, show me afterwards if you're not sure. So n will be n1, which we worked out to be minus 3t divided by square root 5 I, plus n2, which was 6t divided by square root 5j, plus n3, which was 10 divided by square root 5k. And don't forget, all of that was, I built this square root into the original expression. Give me 1 second, Christian. I decided that n was n1i plus n2j plus n3k, all divided by this whole thing, so I've got to restore that. And so if I just kind of basically multiply top and bottom by square root 5, n is negative 3ti plus 6tj plus 10k divided by the square root of 5 times the square root of 20 plus 9t squared. Or you could even just write that as the square root of 100 plus 45t squared if you prefer to have it as a single square root. But this will be your answer for n. Christian?
Yeah, how did you get the 10 over 5k? I was trying to do the k, and the answer I got was there something I was supposed to...
I've erased it now, but you should have got, when you cancelled, the t cubed terms should have cancelled, so you should have ended up with this when you simplified it.
Well, that's look a little different what I got. Let me see. 20 and 16 is 120 and... Hold on.
Just check your numbers, see. I think it'll work out. If not, ask me at the end. What do you think, because obviously we've gone through a lot of work here, and I will point out in this particular one, this one actually, believe it or not, is not that bad compared to some others. In the sense of this one, actually, if you'd done the t prime divided by magnitude t prime, it'd have been about the same. But you'll see in the homework, especially questions? Where's it gone? Completely lost it now.
Yeah, I don't understand what numbers I could have gotten wrong for.
Let me look at it at the end. Christian, let me just kind of get this done. Why have I completely lost the questions I'm looking for? All right, so 35 to 40. Sorry, I was misreading. It's because they're giving specific values of t as well, so you can actually evaluate. With some of those, because they're slightly more complicated, I mean, you can compare and contrast if you want, but this approach of finding the various components of acceleration, substituting into find n, is certainly the way I would choose to do it. But when you get to the end, obviously you've got that. How do you think you could check your answer? What was it, Alex? I can hear you through the mask. Well, yeah, you can, although that wouldn't be, you know, to check an answer, you're really hoping for a fairly quick check. But what two things do I need to be true about n for this to make sense? Has to be orthogonal to t, right? So one thing I can quickly do is just go back and think about what t was, which in this case was 2ti minus 4tj plus 3. Oh, sorry, I cancelled the t's, didn't I? So let's get rid of that. Was 2i minus 4j plus 3tk all over the square root of 20 plus 9t squared. Well, to be honest, the denominators don't really matter. If I do the dot product at the top, notice I'm going to get minus 6t plus 24, sorry, minus 6t minus 24t plus 30t, which is 0. So that checks out. Those two vectors are orthogonal. What's the other thing that has to be true about it? Well, it is, but that was the other way to possibly work it out. That's definitely not a check. That's an entire method to determine n, if you like. But there are two things that need to be true. The whole point of n is two things are true. One is that it's orthogonal to t. What's the other thing that has to be true about n? What's his name? When I write n, what's the actual name of that thing?
Normal.
But the full name of it is the principal unit normal vector. So what can I check? That it's got a magnitude of 1, right? So if I think about magnitude here, that'll be the square root of 9t squared plus 36t squared, which is 45t squared, plus 100, which will then cancel that on the denominator to give me 1. So if you want to check whether your answer's right, mentally it's not that much work to check that t dot n equals 0 and that the magnitude of n is 1. Because those two things, if those two things aren't true, then it's definitely not the unit normal vector. And if they are, then frankly it must be. There's no way that's going to accidentally happen. So those are two things you can run as a check to decide that you've pulled this off right. Let's say no one step in that as anything particularly difficult. There's just a lot of it in a fairly structured order. So it's the kind of thing you definitely want to practice. So when you go through the 12.4 homework, You see, anytime you see a question with only I and J, that should be easy, right? It should not be much work to work out T and N and to do anything they ask you to do. The second that IJK gets involved, like say 35 to 40 are kind of your questions to really practice this. That's when you need to be a bit more pragmatic in the way you go about finding these things. And the question may just ask you to find A sub T and A sub N. Make sure you read the question. Sometimes it just says find your normal component of acceleration. Because there are certain contexts where the only thing you really care about is the normal component of acceleration. Because that's going to determine how quickly you're cornering, you know, how tight a turn you're taking or whatever. So try. We are now basically a day behind, but we'll catch up. We'll work it out. I'm not particularly bothered. We'll do 12.5 tomorrow. We may get it all done in a day, although I allowed 2 days. If not, we'll work that out. I may end up pushing the test back a day. We'll see, and catch up another time. So. We'll see how it goes tomorrow, and I'll make a decision then. So. All right, any questions? Ashley, you good? Hopefully I wasn't breaking up the whole time. I'll record this. So this goes back to the original formula for arc length. So I think this was back in chapter 7, I think. Yeah, 7.4. If you do kind of go all the way back in the book, page 475, this is where our original formula for arc length came from, where it was the integral from A to B of the square root of 1 plus f prime of x squared dx. And if you remember back then, only a fairly limited number of functions gave you something usable. At that time, you got some quite weird functions in the homework because they were the only ones that actually gave you an integral you could evaluate. And then in section 10.3, so this is page 713, the arc length reappeared, but this time it was in terms of parametric coordinates, where it was the integral from A to B of the square root of dx dt squared plus dy dt squared with respect to t. So we did also do it in polar coordinates, but that's not really relevant to what we're doing now. But the point I want to sort of drive home is we now recognize this in vector valued functions, you know, when r of t rather is xti plus ytj, then the magnitude of r prime, because remember r prime now of course is dx dti plus dy dtj. And so the magnitude of r prime is the square root of dx dt squared plus dy dt squared. And so that thing that appears in the integral for arc length in parametric coordinates is now just the magnitude of r prime. And so that gives us just, it's not a new formula, it's just a new way of writing the old formula, which is that arc length now can be written as the integral. You see this on page 855. Arc length is now the integral of the magnitude of r double prime with respect to t. And so when you get arc length questions now, you can basically use the chapter 10 formula, but condensed into a more easily written form. And don't forget, of course, magnitude r prime in the context of position is speed, which kind of makes sense because basically what we're saying is distance equals speed times time, which is obviously a nice easy formula, presupposing that your speed is constant. If your speed is not constant, then you can't use a multiple, you have to use an integral, and that's basically the integral. So your distance traveled, S, is your arc length. Distance traveled along a curve is the integral of speed, magnitude of r prime. So there are some questions on that, but I'm not really going to dwell on those because, like I say, it's really nothing that you've not done before. It's just written in a slightly different way. The only thing that's different from what's gone before is back in chapter 10, this was very definitely 2 dimensions. This was a curve in the plane. This formula that I've just written down here is equally applicable to a space curve, right? That's independent of dimensions, really, that formula. It works just as well in 2 and 3D, and it, you know, harking back to that presentation we did on dimensions, it in theory would work if you had a 4-dimensional vector as well. I couldn't draw it, I couldn't picture it, but it would still be the arc length of a 4-dimensional vector. So you could still actually compute the length even though you couldn't visualize what it represented. So that's the first bit of section 5, and that's the, not the easy bit, but the reappearance of an old idea bit, let's put it that way. But it also helps us establish something called the arc length parameter. Oh, hang on, I'm getting something from Asher there, or was it? Yeah. If I was doing the formula, yeah, plus dZdt squared, correct, absolutely. That's, you'll see that in the book. Yeah, Asher. Now, the point before we get to what it actually is, let me kind of give you the concept of why we're doing it and where we're going with this. So we're going to be looking in this section at the concept of curvature, how curvy a path is, basically. Because that, when we're talking about motion, curvature is going to have a big influence on what kind of forces are required for a motion to occur, right? The sharper something has to turn, the more normal force has to be exerted to make sure that happens. All right. So let's just imagine, let me take kind of a curve here. Let's imagine we've got this curve. Hopefully you are intuitively got a feel for which parts of that curve have higher curvature and which have lower curvature. Hopefully you will be content with me saying to you that this bit of the curve has very low curvature. This bit has very high curvature, right? This bit's almost as high, but probably maybe not quite. It's not quite a sharper turn. Intuitively, does that feel okay, me making that statement? I haven't quantified it in any way. I haven't even really qualified it in any way, but that's what we're kind of going to look at. So what we'd like is to create some measurement, some quantifying process that assigns a curvature, assigns some numerical value to the curvature of some path that we're following, with the expectation that the higher that number, the more curved this path is. One way you can sort of recognize curvature is, remember back in Calc 1, we spent a lot of time on tangent lines, taking a point on a graph and trying to find the best straight line fit that you can. That's what a tangent line is, right? Well, something else you can do with curves that we haven't done before, but we're about to, or at least plays a role in what we're about to, instead of trying to fit the best tangent line you can to a curve, trying to fit the best circle that you can to a curve. So like here, I might try and fit this circle, like the circle that best matches the curve at some given point, what we call the circle of curvature. Whereas if I tried to, you know, it probably is an unwise idea, but if I tried to do it at this point, well, the circle of curvature here is huge, right? I'm not even going to fit it on the screen. Whereas down here, my circle of curvature is pretty small. So just like you can try and find the best straight line possible to represent the graph at a point, you can also try and fit the best circle you can at that point. And obviously when it's a straight line, when it's a tangent line, the thing that you are in control of to some extent, the thing you're trying to deduce is the slope, right? The only question you really have for a tangent line is what slope should it have? I know the point because the question tells me the point, what slope, and that's what the derivative tells me. Well, the only question I've got for a circle is what radius should it be? Right? Once I've got a point, the question really is how big or small is that circle? And that's going to be that's going to sort of form the measure of what we call curvature, except of course, not quite, because the more curvature, the smaller the radius. So they're kind of inversely proportional. I want curvature to be a higher value, the more curved, you know, the more strongly curved my point is, but the more strongly curved it is, the smaller the radius will be. So my curvature is kind of inversely proportional to that, the radius of the circle. But that's kind of the setup that we're going for. So how do I do this? Well, let's go and do another curve. So let me again put something up. Okay. So how are we going to quantify curvature? Well, bear in mind what we've been dealing with here. You know, to be given the curve, we'll have r of t. And we've used that to create r prime and r double prime, and then recently the unit tangent vector, right? So each point has a unit tangent vector, right? This point here has one, this point here has one, this point here has one, and so on. And so maybe that's a way forward for curvature, because what we're basically looking for are places along the curve where the unit tangent vector changes quicker, right? If you haven't got much curvature, then the unit tangent vector is changing quite gradually along that bit of curve, right? Whereas if you've got strong curvature, you know, here, for example, here's the unit tangent vector, and just a little further ways round, the unit tangent vector has changed sharply, because that's a much more strongly curved part of the path. So the first instinct for curvature might be the rate of change of the unit tangent vector. That might be the thing that springs to mind as a possibility. The problem with that, though, is that as set up, r of t, we don't know how much graph is being covered by each unit increment of t. For example, and I'm going to draw a new graph here because this one's going to get kind of too messy. But so that's kind of the setup, and this is what I might think makes sense, rate of change of tangent line. But as I'm going to show you on the next screen, that doesn't quite make sense, because how do I know? Go back to my curve. Let's imagine that you know, this is t equals 1, and this is t equals 2, and this is t equals 3. And because every value of t gives you another vector, another position vector to another point, this is t equals 4, and this is t equals 5, and this is t equals 6, and this is t equals 7. You know, for example, because you know, there's no reason why these t values should be equally spaced along the curve. Almost certainly they won't be as given. But notice the problem here is my unit tangent vector here from t1 to 2, that's quite a significant change. Like that unit tangent vector has turned almost 90 degrees. Right, I've seen a decent change between the rate of change of that as t increases 1 unit from 1 to 2, compared with here, between t equals 5 and t equals 6, there's actually very little change in the unit tangent vector because those 2 points happen to be so close together. So what I'd actually be finding, if I considered curvature to be the rate of change of the unit tangent vector as t increases, I would actually get the result that there is a stronger curvature here than there is here, which doesn't make any sense. Right? That's going to give me misleading results because the suggestion of what the rate of change is might not actually reflect what the curve looks like. And so what we do is we introduce, and you'll see this on page 856, something called the arc length parameter, which basically means you're picking a new parameter. Instead of t, you're switching t out for something else. You are creating so you'll be given r of t, say t squared I plus t squared j. Right, just for example, really nice and simple. So there's a straight line, right? This is a really easy curve. Just the line y equals x, or the a path along the line y equals x. But the problem is, of course, here when t is 0, you're at the origin. When t is 1, you're at the point 1, 1. When t is 2, you're at 4, 4. When t is 3, you're at the point 9, 9. So these, increasing t by unit values doesn't move you the same distance along the line. You're moving greater and greater distances as t goes from 4 to 5, and 5 to 6, and 6 to 7, etc. So what we'd like is to introduce a new parameter s, which will be a function of t. It will be it's a bit like making a substitution, really. When I write something like u equals x squared as a substitution, I'm just introducing something instead of x that relates to x somehow. And here, I'll just put it in as the result. What if I'll let s be t squared? Right, now I'm just saying it here. I'm not showing you why it is. I'm just kind of making that. So if I make s equal to t squared, that means now that r, not expressed in terms of parameter t, but this new variable s that I've introduced, would be si plus sj. In other words, when s is 1, when s is 0, I'd be at the origin. When s is 1, I'd be there. But when s is 2 now, I'd be at the point 2, 2. And when s is 3, I'd be at the point 3, 3. And when s is 4, I'd be at the point 4, 4. So notice now, increasing s by a value of 1 moves me the same distance along the line, regardless of which particular spot I'm at. And that's the aim of the arc length parameter, is to create a new vector value function, or at least a vector value function in terms of a new parameter, such that increasing s by 1 will always move you the same distance along the curve. Right? And you'll see the formula for s in general on page 856. S of t is basically the arc length parameter, but expressed as a function of t. So it's the integral from some constant a, any constant a, basically, of r prime of u. Oops. That's not what I meant to have there. Magnitude of r prime of u with respect to u. The reason it has to be expressed in terms of u, sorry, the u, r is the vector value. I've underlined the wrong thing there. The reason why it has to be u and not t is because u is a dummy variable, right? I'll integrate that with respect to u and then sub in my limits, and my limits need to involve t because that's overall what I expect my function to be. So in effect, that is just arc length, but a generic version of arc length going as far as some value t. So it's expressed as a function of t, because if you've got a curve, you start at t equals a, and you go in as far as you want. You know, you pick the endpoint t, and it will give you the arc length. But that arc length parameter will standardize your curve so that you are going equal distances in equal increments of s. So that's the point of the arc length parameter. So what that will do for any curve, if you work out s, so bear in mind, you're always given r of t, right? That's the start point for any question. So if you work out s using this formula, and then plug that in, so that instead of t now, your function's written as a function of s, what you will have now when you graph it is that, you know, s equals 1, s equals 2, s equals 3, s equals 4, s equals, I should have, make this a bit more curved. S equals 5, s equals 6. So now these distances between the points are all the same. You standardize that distance, which means now if you're measuring not the derivative of t with respect to small t, but with respect to s, now I'm getting what I want, because if changing from s equal 1 to s equal 2 doesn't cause that big a change in my tangent line, then it's not that curvy. Whereas notice from s equal 5 to s equal 6 is a dramatic change in tangent line, as I would hope it would be, because that's clearly the sharpest curvature or the greatest curvature on the path. So this thing is what we call k, the curvature of the path. And k is going to help us. There's a whole side issue of finding the circle of curvature, which is what I talked about before, fitting a circle to the curve as best you can. And the book talks a bit about that, but I don't really want to dwell on that so much. You'll see it on page 860. I do bring it in. But long and short of it is, if you want to draw a circle, the circle of best fit to a curve, the radius of that circle should be 1 over the curvature, right? So the bigger k is, the smaller your radius of curvature is, which kind of is what you'd expect. So the questions are there in the book, but I don't really want to necessarily do that. Notice it's actually not really necessary to find s. I introduced s to give you the concept, to justify the definition of curvature. This is why k has to be, or it doesn't have to be, but why it makes sense for it to be what it is. But that doesn't mean that in every question you need to actually go through the process of finding s, because of course the rules that we saw in parametric equations mean that this is the derivative of t with respect to t divided by the derivative of s with respect to t. Right, back in chapter 10, when we were doing parametric equations and calculus, we established that that's how those things worked. Well, this can be written as, and it's the, by the way, sorry, when I wrote curvature down, I missed out. This should be the magnitude, because obviously derivative of the tangent vector with respect to something is itself a vector. Well, curvature is not a vector, it's a number. So I should have put the magnitude in here. And so these are the magnitudes of these things. So this is t prime magnitude. And of course, don't forget what we said just before. We defined S of t to be the integral from a to t of r prime of u. Oops, I did it again. I don't know why I want to underline u so bad. Magnitude du. Well, if you remember the fundamental or the second fundamental theorem of calculus, if you differentiate something that's defined using an integral, then the net result is you just get the original function back. And so ds dt will simply be r prime of t magnitude. And so that's the formula for curvature directly in terms of what you're given in the question R. We know how to find the unit tangent vector t, and so we can compute the curvature that way. And you'll see another formula, the homework actually asks you to, there's several formulas for curvature. The homework asks you to derive a few of them, but probably the most useful one, also in the box on page 859 right next to this, is the magnitude of r prime cross r double prime. Like I say, you're actually asked in the homework to show why this is the case. I'll let you think about that. Divided by magnitude of r prime cubed. And that's probably the most direct formula for computing this. But if you do look in, where is it? Page 863, where the whole of page 863 is really just a summary of the chapter. Defining velocity, speed, acceleration, unit tangent vector, unit normal vector, components of acceleration, etc. At the bottom, you will see 5 different formulas for curvature. Some more useful than others. I would say this one is probably the most useful. It kind of depends on whether you're given a vector valued function, as we've been talking about here. But of course, now you can backtrack and actually make curvature a feature of just ordinary graphs. You know, I mean, now if I go way back to sort of certainly pre-calc 3, you know, if I'm y equals f of x, well, having established this concept, now really I should be able to talk about curvature here as well. We tended to get bogged down on tangent lines, but curvature is still a thing here. And so they give you some formulas for how you can actually work out curvature. If it's not vector valued stuff, it's just graph of a function. And if you need that, you'll be given that formula. Right? You don't have to memorize curvature formulas. That's not the point of them. You've got to be able to use them. So in the test, I'll be giving you whatever curvature formulas you need. Okay. So let me give you an example. Okay, I've got one here. Right, so find, please. If I give you r of t is equal to ti plus t cubed minus 3tj. So this is just a plane curve. Don't forget, you know, cross product isn't generally done on 2-dimensional vectors, but it can be. It doesn't tend to, if you're using it to actually find normal vectors and stuff, it's kind of pointless, because if you're in a plane, then the cross product of any 2 vectors in the xy plane will simply be something k, right? Cross product is always orthogonal to both, and so it must point in the z direction. So in terms of actually finding a vector, the cross product doesn't really have much value when you talk about plane curves. However, the thing I want here isn't the cross product, it's the magnitude of the cross product. I don't really care about the direction. In fact, I know the direction. What I care about is the size of it. And so cross product does sometimes get used here. You can do that, just put in 0k as your term. But see if you can work out the curvature at any point here, t, by using the r prime cross r double prime magnitude divided by magnitude of r prime cubed. See what you get. So there's my r prime and r double prime. So if I do my cross product, pretty simple, because obviously there's no I or j components. The zeros wipe that out as expected. I expect the result to just be a multiple of k, and you can see this time it's 6t k. That's my cross product. The magnitude of r prime is going to be the square root of 1 squared plus the 3t squared minus 3 all squared, which I will write out, although I'm going to go back to that form soon. So that'll be 9t to the power 4 minus 18t squared plus 9 plus 1, so plus 10. And so my curvature here will be the magnitude of my cross product, which is just 6t, divided by my square root, or that square root expression, but cubed. Remember, it's r prime, magnitude of r prime cubed was on the denominator for my formula. So it will be 9t to the power 4 minus 18t squared plus 10 to the power 3 halves. Right, that's the formula for curvature in terms of t. So wherever you are on the curve, work out the value of t, plug it in, that'll give you the curvature. Okay. Let's actually think about that in terms of interpreting it. Say, bear in mind, this is a nice simple analysis in the sense of it's a plane curve. There's no k component, so this is really the graph of y equals x cubed minus 3x, right? Because x is t and y is t cubed minus 3t. So let's think about that graph. We've just said the curvature is 6t divided by, this time I'm going to go back to the 1 plus 3t squared minus 3 all squared version to the power 3 halves. So when I graph this, y equals x cubed minus 3x, looks like this. Well, let's think about my curvature. That expression on the denominator. What is the smallest value I can get? With all the different t's I could choose, what's the smallest that denominator can be? No, that's why I rewrote it like this rather than left it in the other form. 1, right? If t is 1, then the parentheses will be 3 minus 3. And if something's squared, basically anything squared bottoms out at 0, right? Can't go less than 0. So this will have its maximum value. Now, to do the full maximum, I'd have to do calculus on it. I'd have to actually do, dk dt equals 0 to get the true maximum. But it's fairly easy to see that t equals plus or minus 1 will give me the maximum value here. If t's not those two values, then that denominator is getting bigger, and so the curvature is getting smaller. Well, where are they? If t is, remember, r of 1 is I plus t cubed minus 3t, so I minus 2j. In other words, it's here. It also happens to be a relative minimum on the graph. And r of negative 1 will be minus I plus 2j, which is here. Well, that's kind of reassuring, right? Because those 2 points look like they've got the greatest curvature here. Whereas over, for example, this point, this might be like, I don't know, t equals 4. Something like that. Well, if t equals 4 here, that denominator is much, much bigger. And so the curvature is much, much less. I mean, obviously the top's linearly increasing with t, but the bottom is growing at, with t squared. So the further I move away from that point, the smaller the curvature is becoming, which kind of makes sense when I look at that graph, right? This, by the time you're at these points, there's very little curvature to that. It's still curving. It's never straight. It'll never be a straight line. The curvature will never be 0, because k equals 0 means a straight line, right? but it will be getting less and less. So you can kind of see how the solution fits here, if you like. Notice I can work out, what about the origin? What's the curvature at the origin? So my curvature at these 2 points is 6. What's the curvature at the origin? Well, what's t at the origin? 0, right? So the curvature, 0. Why? Because, well, what else do I call the origin here? Back in Calc 1, what's my description of the origin? Point of inflection, right? Well, basically, point of inflection is where curvature is 0, because you're transitioning from curvature one way to curvature another. You're changing concavity, remember? So there's a lot of old concepts here reappearing with new names. You're not going to see concavity and point of inflection referred to here, but essentially they're there underneath it all. Curvature of 0 is either a straight line or it's a point of inflection. And negative, we haven't talked about negative and positive curvature because we've made curvature a positively valued thing the way we set it up. But you could go a little further and actually classify curvature whether it's concave down or concave up. We're not going to do that, but it's not too much of a stretch to imagine doing that. So there's a lot of similarities. Now, the minute you move into space curves, you're going to lose all that. That's why I picked a plane curve. If you've got a vector value function with I, J, and K, all of this still holds true. You still compute the curvature and everything, but now you won't be able to match it up with things like points of inflection or anything like that. It's going to be a different story. But underneath it all, the concepts are still kind of lurking there. They're just a bit deeper now. There's still one last thing I want to talk about, which I think I'll do Thursday. So I think I'm going to push the test back a day, if that's okay with everyone. I mean, I want to check because I have said that's when the tests are. So the test would now be next Monday rather than this Friday. Is everyone okay with that? Asher, do you have an ETA on your return? Monday. Okay, so that would definitely work out better if you'll actually be back Monday as well. You'll see that the next chapter I built 2 review days in, so I'll probably just end up cutting one of those, so to try and get back on track. But I want to talk a bit. There's a bit more to say about curvature, and I feel like this section could use probably a review day and a half to sort of make sure everything's clear. So Thursday I'll just be finishing this and start a review. Friday I'll be more review. Test Monday. All right. Any questions? Good. I'll see you Thursday. Oh, I'm sorry, actually, I just realized I forgot to turn my mic on. Sorry about that. Thank you for pointing that out. But if you look on page 856, you'll see the formula we looked at yesterday, the derivative of the arc length function. Because of the way the arc length function is defined, this thing here, the magnitude of r prime, is ds dt. Right, it's the derivative of the arc length function. And so what we've got here is actually the second derivative of the arc length function. So because of the way we've set up the arc length parameter and curvature, although curvature actually doesn't have anything to do with this one, the tangential component of acceleration will be just the second derivative of the arc length parameter. Meanwhile, and probably more importantly, a sub n, well, the formula for a sub n was magnitude of v times magnitude of t prime. There were plenty of formulas for a sub n. It gave you 4 different versions back on page 850, but that's one of them. But notice, of course, here, well, magnitude of v is what we were just talking about. That's ds dt. And magnitude of t, well, let's take a look at this formula up there. Magnitude of t prime is just the curvature times magnitude r prime. So this thing here is just the curvature times that same thing, magnitude of v, magnitude of r prime again, so ds dt again. In other words, I've got k ds dt all squared. So the result of these definitions of arc length and of curvature, as applied to our general formulas from before, give us those for my components of acceleration. So put all that together, and what I have is that A, when I'm specifically talking about a path and looking at curvature and arc length parameter, is d2s dt squared t plus k ds dt all squared m. So that's acceleration expressed tangentially and normally in terms of curvature and arc length parameter. Now bear in mind here, s is in effect distance traveled. Right, that's what the arc length parameter basically is looking at. So the derivative of s with respect to t is really just your straight line speed. If you're on a curve, it's the equivalent of the speed you're doing in whatever direction you're pointing if it was a straight line. And d2s dt squared, second derivative of that, is basically your straightforward acceleration. Like what acceleration you're doing in a straight line, ignoring anything that's causing you to turn left or right. But ultimately, and bear in mind, of course, since force is mass times acceleration, then it's just m times these things. So let's imagine you're on some curve that's given by r of t. Well, at some given point, your acceleration will have a tangential component of d2s dt squared and a normal component of k ds dt squared. Or more accurately, in terms of a physical use, those are what you're going to require if you are to stay on that path. In order to stay on that path, you must be able to experience those two components of acceleration, because that path is determined by those two components of acceleration. Now, the straightforward one, this tangential component, but I mean, let's imagine this is a car driving on a road, right? That's just basically the force that's driving you forward, right? That force is going to be generated by whatever is causing the motion. So if it's a car, then the engine is creating that force, right? So whatever your engine can do, then that's the force it can generate. So short of that being, you know, incredibly strong acceleration, then that's what your engine is going to be able to provide. The trickier bit is the normal component of acceleration, because that's not being generated by anything in the car, because that's not pointed in the direction that the car's going. The car can only generate a forward motion. So the turning can only be generated by friction from the surface, right? Anytime two objects are in, you know, interact with each other. Did I miss anything? Okay. Anytime objects interact with each other, then there's going to be an action and a reaction from them. And if it's one stationary object or one moving object, that's going to be a force of friction. And so basically, to stay on this road, the road needs to provide, in terms of a force of friction, this force. But there will be a maximum amount of friction that the road can generate. Right? You can't just indefinitely create friction. Friction is a property of the road surface and the whatever's coming into contact with it. So your tires, if it's a car. So, you know, you can, if you have some control, you can increase the friction by making the road surface rough or by making your tires rough. But there's a certain amount of friction that you can't exceed, which means that this combination can't get past a certain amount if you want to stay on the road. And it's going to depend on two things, right? It's going to depend on K, the curvature, in other words, how tight the turn of the road is, and then ds dt, which is your speed. It's the first derivative. In fact, your speed squared. So basically, at any point on the road, well, let's say there's a finite amount of friction available. If your curvature is small, then that's okay. Your speed can be a bit bigger, right? Because K is smaller, meaning ds dt can be bigger. Notice the mass has a bit of an impact. You know, you increase the mass, you're increasing how much friction is required, but friction will actually often depend a bit on the mass as well. The heavier the object, the more friction generated. So the mass is a bit of an illusion, because if you make mass bigger, you'll usually increase the friction force too, up to a certain point. But the other two, well, K is a property of the road, and ds dt is your choice of speed. So if you're on a straight part of the road where K is small, then you can get some speed up and you'll be fine. But if you come to a tight turn where K gets much bigger, you're going to have to pretty significantly reduce your speed, or you're not going to be able to provide as much force as is needed, right? If your speed gets too high and the curvature gets too high, then this amount that you need, the road can't provide. You'd need more frictional force than is available to you, and so basically you'd slide off the road, because in effect the car will find a path with the amount of curvature it can cope with. And so if the road looks like this, but you're going too fast, then what your car's going to do is something like this, because that's the most curvature it can deal with. So it finds a path with less curvature because the speed is greater than what it can actually, what the force can actually, or what friction can provide as a force. And so you slide off the road. So you kind of see what you know by common sense is you come up on a tight turn, you slow down. But notice they're not proportional. If the curvature, like if you double the curvature, you don't halve your speed. You have to quarter your speed, because the speed is actually there as a quadratic rather than that. So You know, that's what's the cause of some accidents is people slow down, but they don't slow down enough because they don't compensate for the fact that it's actually v squared, your speed squared rather than just your speed. So those are the components of acceleration once you start expressing the path in terms of curvature. But like I said, don't think of this as what the car generates. Think of these as this is what you need. Make sure that the surface can provide it. Now, you can do things, like I say, you can make the surface rougher, you can increase the friction, and so you'll make the total of this amount bigger. You increase the kind of the supply, if you like, of force. The other thing you can do is, for example, bank the road. Because if you bank the road now, if your car is on incline, now the reactive force coming off the road this way actually already has a horizontal and a vertical component. So this component is already helping you turn. So now, as well as friction, you've also got some of the weight reaction from the road also helping you turn. So, you know, you build a racetrack or something, you bank the road on a sharp turn because that allows you to go much faster around the bend because you're providing some extra force for the normal component of acceleration. But if it's a straight road, not so much. And of course, if it rains and there's a lot of water on the road, well, you're significantly reducing the friction. And so when it's wet conditions, you're going to slow down even more because you're not getting as much friction from the road. So the supply that is available to you is even less. And so you're going to reduce, since you can't change the curvature, that's just, the curvature is fixed by whatever road you're driving on. The only thing you can change is slow down even more, reduce dSdt even further. So, you know, wet conditions, slippery conditions, you're much more likely to skid if you don't go even slower. And so that's what the end of section 5 is showing you. And then there are some problems where kind of that's put into place. So you know, you'll see in the homework some questions somewhere. I saw one before. Okay, so 78 is kind of a formula approach, but 79 and 80 would be word problems along that line. Vehicles driving at a certain speed on a certain road with a certain curvature. You know, how much frictional force will be required, or what speed is necessary to stay on the road? That kind of question. So that's the kind of word problem you might get. I'd make that a take home if I was putting that on, but that's a kind of an application thing here. So, any questions about that? Happy with it. I never did ask if there are any homework questions at the start. Does anyone have any? In terms of reviewing, I can go through anything that you want to see. Okay. So, recap then. I think what I'll do is, right now, I'll just sort of recap everything we've done from this chapter to remind you of the material, and then tomorrow we can work problems. Like I said, every time, review sessions go way better if you're bringing questions, right? Me deciding what you might benefit from seeing is not really going to help that much. So section 1 was just the concept of vector valued functions, right? I didn't miss anything from Ashley there, did I? So section 1 just introduces this thing that the entire chapter has been built on, so you should be comfortable with it by now, where I'm giving some function whose input is still a scalar quantity, some parameter t, but the output is a vector. So for example, I might have t squared I minus 3tj plus sine tk, something like that. Now, every value of t will produce a vector. You can consider that to be a position vector going from the origin to some point in space, and the curve that joins all of those points together is the curve associated with that vector valued function. You can kind of think through a bit about what it would look like. For example, here, well, I'll tell you what, I'm going to change this slightly for, let's make this ti ti plus t squared j plus sine tk. So I can think about the xy plane, the xy trace, if you like. X is t and y is t squared. In other words, y is x squared. So the xy trace is this parabola. But really, I'm not thinking about a two-dimensional curve. I'm thinking about a three-dimensional surface, and so it will be the parabolic cylinder of that coming out of the page. So it'd be more of this shape. Except, of course, it's not that whole thing, because what I'm describing is a curve. So basically, it would be a curve inscribed on that cylinder. And what would it look like? Well, the z component, sine t, of course, is just going to oscillate between -1 and +1. And so basically what I'm looking at here in 3 dimensions so I got y equals x squared, which is this, oops, no, it's not, let's try that again. Which is this parabola here. But it's a surface, so that's kind of a parabolic cylinder going straight up. And I'm going to, my path is going to basically, exactly how it does it, I'm not sure, but it's basically just going to bounce back and forth along that between -1 and +1 on the z axis. So it'll kind of gradually move around that parabola, but going up and down as a sine wave. So if I can try extending this a bit here. And so it's kind of going to go something like, come around the corner and then back again. So it's kind of a sine wave that's sort of been inscribed along the parabola as you come around the corner. I don't know if that's helping or not. That's not the best diagram, but that's the curve that's being described there. So you can usually work out roughly what kind of curve is being described, but drawing it is often a lot more difficult than visualizing it. But this curve is kind of going round a corner, going up and down. It's like a sine wave that's been bent around onto a parabolic cylinder, if you like. Now, in section 1, that was a very abstract idea. It basically just created a space curve for you, or possibly a plane curve. If there'd been no k component, then obviously it just creates that parabola, and that's a much simpler idea, right? Thinking about that, drawing that's a whole lot easier. But the minute you throw a k component in and have a space curve, it becomes a lot harder bit harder to picture and a lot harder to draw. All right. But in 12.1, this is a purely geometric idea. It's basically a way of defining a curve in space, right? You think back to the previous chapter, the previous chapter, we basically spent our time in 3D on straight lines, which we did parametrically. But after that, it was planes and two-dimensional surfaces, right? So most of the previous chapter was two-dimensional surfaces, you know, hyperboloid of one sheet or an elliptic cone or something like that, with a very small amount of straight line. Really, in some ways, the straight line should have been saved until now, because this chapter is more about lines and curves in space rather than surfaces. And it kind of comes the opposite way. You'd think lines and curves come first, surfaces second, might seem like the obvious way of doing it. But because these lines and curves are generally sort of inscribed on surfaces, it's easier if you already understand how surfaces work to then think about how you might put a curve. You know, if I give you an elliptical cone, how you could then draw a spiral around it or something like that. So although it might not seem it at first, it kind of does make more sense to do surfaces first, then curves. And I say the book messes that up even more by doing straight lines short quickly. But really, you know, back in back in chapter 11, you know, a straight line was something like this. Right? We wrote parametric equations. Well, basically, that was just a placeholder for now. R of t would be 5 minus ti plus 2 plus 3tj plus 1 plus tk. Right? That literally is the exact same line, just expressed as a vector valued function. But it's a more useful thing because this has a sense of direction associated with it. Back in chapter 11, that was just a line floating in space. This now is a directed line, because as t increases, you're definitely traveling one way along the line, and so there's a sense of motion, and we can start talking about r prime and r double prime. Now again, back in section 1, they don't really get into r prime and r double prime too much because that's pure geometry. And short of if we were going to start thinking about things like points of inflection, maximum points, minimum points, well then we might be interested in it. But really it's the curve itself. So section 1 doesn't really get into derivatives, right? It just defines vector valued functions, how they might be curves. You know, example 4 in the book, page 822, shows you how it's a curve on a surface. In fact, you can, if you want, as they do there, create your curve by having two surfaces intersect with each other. That will create a curve as well, curve intersection. And then it briefly talks about limits and continuity. Section 2 introduces the idea of calculus to this, differentiating vector value functions, integrating vector value functions. Again, at the moment, purely geometry, right? This is very abstract, doesn't have any real physical meaning at the moment. It's just a curve in 3 dimensions, and you can find r prime and r double prime. Right? And that's all it's really talking about back in section 2. Just gives you some practice, but it's pretty much just practicing your old calc skills, differentiating and integrating. Section 3 is where we actually start doing something with it. Section 3 gives an application to this. It says, if this vector valued function happens to describe position of an object, and therefore also basically describes its path, then r prime describes its velocity and r double prime describes its acceleration. And because of that, we can actually think about forces acting on that. So be clear on the fact that section 1 and to some extent section 2 are just, you know, math floating in math world with nothing to do with anything else. Section 3 is where they anchor that to having some value in terms of physical meaning, position, velocity, acceleration. That's one way you can use R prime, and R double prime, if and only if t is specifically time. Right? T doesn't have to be time. T is just some parameter. But if t is time, then everything now takes on a meaning. R of t describes the position of an object at any time t, and therefore the path that it is traveling and the direction it is traveling on that path. R prime describes the velocity of the object, the rate of change of position, and the magnitude of that we call speed. And R double prime describes the acceleration. And the value of that, of course, is mass times acceleration is force. And so that will help us determine either what forces must be acting on that object, or what forces we need to provide in order to make the object follow that path. So section 3 is where we actually give some application to this, including projectile motion. We talk specifically about that because that's one use of this. Projectile motion, basically motion that happens in a plane, and how you can follow that. Projectile motion in an idealized form always winds up being a parabola. Right? In effect, any object that is thrown with some speed at some angle will follow a parabolic path until it lands. In reality, it's not quite that, because the minute air resistance gets into play or whatever, that's different. Obviously, if projectile motion is only if the object has no propulsive force of its own, right? I mean, if a plane takes off from a runway, it doesn't come down instantly in a parabola because it's got its own engine forcing it up, right? Projectile motion is only for objects that have been thrown, but then themselves have no propulsive force. They are now only subject to gravity and nothing else. And they will always follow a roughly parabolic path down to ground level. So that's what section 3 is looking at. And then section 4 introduces this idea of tangent and normal vectors. And again, that's really a physical application. Because if an object is traveling along some path and you're looking at what forces are making that happen, or what forces it is being subject to, those forces will inevitably always be either tangential to the motion or normal to the motion. Right? So I and J aren't really much use to you, because almost certainly I and J are neither tangent nor normal to that motion. So if your object is following some path here, and it's at this point here, well, the forces that are going to be relevant are either going to be in this direction or they're going to be in this direction. Not horizontal and vertical, but tangent and normal. And as I move around the curve, those directions will change. Once I've moved around to this point, now the forces are tangential, and notice actually my normal one has flipped here because I've gone past the point of inflection. So here's T and N in the first case. They've almost swapped places by the time I've come around to the second one. So T and N themselves depend on where you are. So they are themselves vector valued functions of T. And section 4 is all about how you find those. If it's in the plane, if it's 2 dimensions, then it's fairly easy. To be honest, T is always fairly easy. Remember, T is always just R prime divided by its own magnitude. Regardless of whether it's 2 dimensions or 3 dimensions. You'll do the same thing. N is the hard thing, which is frustrating because it's also, as we were talking about with the motion, N is normally actually often the more important of the 2 forces, or 2 components of forces, because N is what causes things to swerve or turn or change direction. If it's 2 dimensions, fairly easy. If it's 3 dimensions, quite complicated, as we talked about. All right. And then finally, section 5, what we just did on curvature. Any specific questions you want to ask about? Because this is normally considered a reasonably hard chapter, but I can only answer questions that you give me. So. Hello.
Questions, they're basically going to be about, like, so I feel like everything just has to do with, like finding R prime, and everything includes R prime.
Yeah, I mean, most of the questions will start by giving you R, and yeah, typically you will find R prime, possibly R double prime, and then do stuff with it. And like I say, you will be given a formula sheet, because there's quite a lot of formulas here. I mean, if you look on, has it gone? Looking at it yesterday. Page 863. The whole of page 863 is basically just a series of formulas developed over sections 3, 4, and 5. Now, I'm not saying I'm giving you all of those, because some of them I expect you to know. I expect you to know the formulas for unit tangent and unit normal vector, for example. But I will give you the components of acceleration and the formulas for curvature. But there are several of those. And I do expect you to know which one to use in the right context. Right? So you don't have to memorize stuff, but you do have to know what to do with it when it's in front of you. Like I say, I mean, there are 3 different formulas for A sub t, the tangential component of acceleration. There are 4 different formulas for A sub n, the normal component of acceleration. And there are 5 different formulas for curvature. So you need to have some familiarity with those kind of questions and what's being asked to know which one to use. I mean, that's not to, it may be that you can use more than one. It might be just your decision as to which you prefer. But, you know, I'm not going to tell you, here's one formula for you to use. I'm just going to basically present the second half of this page to you as a sheet and expect you to know what to do with it. But like you say, I mean, one way or another, R prime, or as this, you know, either R prime or V, which of course are the same things, if T is time, right? Bear in mind, you don't see V appear until section 3. In section 1, R prime, in section 2 rather, R prime is just R prime. Doesn't really have any meaning beyond just being the derivative. In section 3, it becomes velocity. But once we've got that practical application, nearly all of those formulas, one way or another, involve either R prime or V. And so quite a few are R double prime or A as well. So yeah, you're right. But so it's what specifically to do with R and R prime and R double prime is what the questions are asking. Yeah. Well, I probably would need a bit more time than I've got left. So tomorrow I'll definitely do a projectile motion. Sure. I'd do it now if I have probably 15 minutes left, but I'd like to go through that in a bit of detail. So, is there any other thing anyone can think of that I don't really want to waste this 10 minutes? I just don't want to start a question I can't quite finish.
Anything like, since n is finding out n is easier than 2 dimensions or 3 dimensions, so you can really just kind of have one of those problems.
I put a 2-dimension one in class and a 3-dimension one on a take home. Yeah, I expect you to be able to do the 3D ones, but not quickly. I'd give you however much time you need to go through that process and check it. So I definitely, and in class, that'd be half the test, really. Well, here's something I'll do right now. So it's not projectile motion, but I'm going to give you A for an object. So let's say this is to the power 2ti plus 3j minus sin tk. And I'm going to tell you that an object has that acceleration vector. It starts at rest from the point, let's say, 1, 1, 1. The ultimate question I'm going to ask is, where is it after 2 seconds? But really, the main bulk to answer that question, really, the question is find power of t. So integrate to find v and work out the constants. Integrate it again to find r and work out the constants. Having done that, then the question is really, okay, put t to 2, see what happens. So in 5 minutes, see if you can work out first what v is, then r is. So if I integrate these, well, first one I'll get 1/2 e to the power 2t, or e to the power 2t over 2 plus a constant. And then I'll get 3t plus a constant. And, oops, I'm going to run out of space here. Third one I'll get cosine t plus a constant. But I know that v of 0, which is c1, sorry, is 1/2 plus c1 I plus c2j plus 1 plus c3k. That's nothing because it starts at rest. So c1 is negative 1/2, c2 is 0, and c3 is negative 1. And so my velocity vector, I now know exactly to be e to the power 2t over 2 minus 1/2 I plus 3t j plus cosine t plus, sorry, minus 1 k. Right, that's the only vector that is 0 when t is 0 and differentiates to that a given in the question.
Okay, I'm a little confused about how you got to the yeah, could you explain like the second, the third thing?
Where the constants come from?
Yeah.
So I'm plugging t equals 0 in here because it says starts at rest. So starts means t equals 0,
Yeah.
and rest means no velocity.
All right.
So when t is 0, v is 0. In other words, all three of these must be 0. Well, if I plug in t equals 0 here, that's 1. So 1/2 plus c1. This will be nothing plus c2. And this will be 1 plus c3.
Yeah, I guess I must have gotten this position confused with like a position of velocity or something.
Maybe. And then if I integrate again to get r, well, this time if I integrate, I'll get e to the power 2t over 4 minus 1/2 t plus a constant. Second term, I'll get 3t squared over 2 plus a constant. And third term, I'll get sine t minus t plus a constant. But I also know that when t is 0, in other words, r of 0, which if I plug that in, plug in t of 0 here, I'll get 1/4 plus c4 I plus c5j plus c6k. Because when t is 0, pretty much all of those functions disappear except for the exponential one. But it starts at the point 1, 1, 1, so that's I plus j plus k. That's the starting position vector. And so that tells me that C4 must be 3/4, C5 must be 1, and C6 must be 1 by comparing these three coefficients to these three coefficients. Does that make sense? You see where that's coming from?
Yeah.
I'm kind of out of time and space, but so that basically now just plug in that C4, C5, and C6 back into here. That gives you your answer for the position vector. So the question might have just said find a position vector, in which case that would be the answer. If the question said where will the object be after 2 seconds, well, now you need to plug t equals 2 in across the board here and evaluate it. But obviously that's going to be messy because sine of 2 isn't is a decimal, and e to the power 4 is a decimal, and so on. So the question will be planned out a bit better than this on the test. But those are the two things this question could have said. Either give the position vector in general or find where the object is after 4 seconds, something like that. Okay, does that make sense? Yeah. That's kind of one example of the kind of thing you might be asked to do. Tomorrow, bring questions. I'll definitely do a projectile motion. Olivia, and then anything else you want to see done. You might, after the curvature problems and the section 5 homework, you might have some of those you want to do tomorrow as well. So. Asher, what did I miss there? This will be more for the position vector, while something else would be for the time. I'm not quite sure your question, Asher. The east. I'm not quite sure what you're asking. This is the problem with like trying to type into this thing, I guess. You might work. Are you able to say the question?
I think you means we're normally trying to find like acceleration, like as time increases, but in this case we're given acceleration, we're finding position.
Oh,
I don't know.
that might. Maybe that's.
Something like that. My understanding.
No, I'm not hearing anything. My volume is always at half. Try again. No, I'm not getting anything. I just, for some reason, I'm not quite understanding. This will be more for the position vector, while something else will be for the time. I mean, everything will always be expressed in terms of something easy to plot. Oh, I see what you mean. Yeah. Yeah, just so, you know, in this case, whatever value of t I gave you, the answer is going to be a mess, because the I component will have e to the power something, and the k component will have sine of something. You know, and I don't want to pick, you know, I don't want to pick pi over 6, because e to the power of 2 pi over 6 isn't, you know, that's just a mess. So, I mean, it's fine. If you've got a calculator, you could just plug them into every expression and come up with a numerical value for I, J, and K. But in a non-calculator test that's coming up, I'll pick something where you can evaluate it more easily. Yeah. Does that make sense? No, it does not have a calculator. Obviously the take-home part, that might have some calculator work, because I have no idea whether you're using a calculator or not there. So, yeah, all right. So I will. Well, I guess I'll see you online tomorrow and then back on Monday. Let's get recording. Review. What are we reviewing?
Well, I'd like to start out by going over how to find the principal unit normal factor, like say question 12.4, number 18.
12.4, number 18 sounds a good place to start. All right, so 18 from 12.4.
Yes.
So R of t here is square root 2 ti. T is outside the square root, notice, plus e to the power tj plus e to the negative tk. Okay. So this is a space vector, rather a plane vector. So let's start by thinking about the tangent, unit tangent vector. So our prime of t here is square root 2i plus j minus e to the power negative tk. Right? Which means that the magnitude of r prime will be the square root of square root 2 squared, so 2, plus e to the power t squared, so e to the power 2t, plus e to the power, or minus e to the power negative t squared. So e to the power negative 2t. This is one that they've set up with one particular thing in mind, but not made it very obvious at all. If we carry on with this, it'll work, but it'll be quite a mess. But do notice that this actually factors, right? This is e to the power t plus e to the power negative t all squared inside the square root. Right? If you FOIL that out, then your middle terms will be e to the power t times e to the power negative t, which is 1. So your outer and your inner terms will both be 1, giving you the plus 2 term. So actually, the magnitude of r prime winds up being something you can write without a square root. And they're sort of building that into their expectations without really making that necessarily obvious. So t here will be the square root 2. Let me write it in that more compact form. The vector that divided by e to the power t plus e to the power negative t. And that's why, to be honest, in this form, because that denominator simplified so much, here you actually would probably be better off doing n as the t prime divided by its own magnitude process. I don't know, you really need to go through the whole thing that we did with the a sub t and the a sub n. Normally, that's the better way forward because the denominator for t is a square root of a somewhat complicated expression, which means that taking the derivative becomes really messy. But if you do get a case like this, which they've very carefully chosen so that the denominator actually simplifies, now it wouldn't be too bad. So I'm sort of in two minds as to how to carry on here, because very much the book is expecting you to do the t prime divided by its own magnitude for n, but only in this particular case. Whereas what we went through for what will be a take-home question isn't that method. But equally, this one doesn't suit that method. So I don't know how well they want to finish this one, because I think it might actually confuse matters rather than help.
What? Oh, at least we could give it a try.
We can, it's just going to take a decent amount of our time and not help you on the test.
So you're saying that...
Because this is a very carefully chosen one, which will be a rare time where a space vector suits this definition for the unit normal vector.
Oh, okay.
Every other one we've looked at and ones we talked about, we said if you're going to do the unit normal vector, you should consider the I think it's run out of power or something. We said we'd do this and sub in everything except the unit normal vector and solve for it. That's the example we did in class, what I pointed you to in the homework, what I said I'd put on a take home. But in this particular case, that wouldn't be the best way forward. But it is just this question. Right. So, you know, any question where the denominator doesn't lose its square root, you would want to go with this second method, which is the one we talked about. This particular question has been very carefully cultivated so that magnitude r prime winds up being a very straightforward function. So in terms of, this would take a good amount of our time and not really give you any help with anything that's going to be on the test. So if you want to see it, Christian, I tell you what, just we'll set up an office hour, or you can send me screenshots and I'll send you back solutions or something. But in this particular case, that's what I would do. I I will find t prime here and plug in. Okay. I mean, it's a good question. It's not. It's certainly an interesting setup, but it's not, because you'll notice that some of the other ones around there do a similar thing as well. That's why they're early on, whereas the later questions involving unit normal vectors come further down the line, and that's. So I can do a different one if you want that does show the more standard method, if you would like. Do you want to see one of those?
Well, I was just about to try number 16.
Right. Well, 16 is a different story because 16 isn't a space vector. So we can definitely look at 16 because that will be a more of an in-class example. So the number 16. So it's giving us Ti plus 6 divided by Tj. And so in this case, R prime will be I minus 6 over T squared J, which means that the magnitude of R prime will be the square root of 1 plus 36 divided by T to the power 4, square rooted. Which, note, I don't really want to leave fractions inside square roots if I can help it. So that will be the same thing as the, if I get a common denominator here, I can then get my denominator at least outside of that square root. So this would be the square root of T to the power 4 plus 36, all divided by T squared. And so T, which will be R prime divided by the magnitude of R prime. So that's basically going to be R prime, I minus 6 over T squared J, multiplied by the reciprocal, so T squared divided by square root 36 plus T to the, oh, right, keep writing it the same way as I did before. T to the power 4 plus 36. And so that will give me T squared divided by square root T to the power 4 plus 36I. And then when I distribute, the T squared will cancel, so minus 6 over square root T to the power 4 plus 36J. So that's my unit tangent vector. Now, it doesn't actually ask for that in the question, just asks for the principal unit normal vector, but there's no way of getting the normal vector without the tangent vector first. Whichever way you go about it, there is no direct path to the normal vector. You either work out T and then do the T prime divided by its magnitude, or you work out the T and use the method we talked about, or in 2 dimensions, as we said in class, you just take your T and switch the 2 terms, changing the sign on 1. All right, so we know that the unit normal vector here, I think the question asks for, will be, we'll change the 2 terms, so now I'll have 6 over the square root of T to the power 4 plus 36I, and T over the square root of T to the power 4 plus 36J. Change the sign on one of them, so either now they're both negative or they're both positive. So I'll put a plus sign here, but I don't know whether to take the plus or minus version of that. N is one of those 2 vectors. And it's not the case that I'm supposed to choose which one it is. Which one I choose will be conditional on what value of T I'm looking at. Some values of T I'll choose the positive, some values of T I'll choose the negative. All right, but in this case, it specifically gives me T is equal to 3. So I'll do that on the next screen. But is there any questions on what I've got there? Is everyone happy with that? That makes sense?
I'm not exactly sure how you got those parts. Like, was there a certain method, like,
Which?
Like the 9nt is supposed to be like the derivative of t over the magnitude of t prime.
So this is what I'm saying to you is there are basically 3 different possibilities for working out n, right? So hang on, is everyone happy with it? I'm going to cut the screen now to write those on the next one. Is everyone happy with what's on the screen here? You probably have to remind me what n was in a second because I'll forget it. But, so 3 possibilities. If you're given in the question R of t, it doesn't matter which possibility you choose. The first thing you're going to need to do, whether the question asks you to find it or not, is to find the unit tangent vector. So there is no path to the unit normal vector that doesn't first need you to find that. Right? From that point, there's then 3 possibilities for finding n, depending on context and the functions involved. Right? So one of them is to use that definition that you just said, Christian, that n is t prime divided by its own magnitude. Right? That's not often the best way. But that question you just asked me, which is why I left it unfinished, was because that would be a rare example where that would be the best way of getting n.
Yeah.
But I'm not going to give you one on the test that does that because that's a very specific type of situation.
All right.
So the 2 usual ways would be if it's 2 dimensions, that if t is xi plus yj, then n will simply be yi minus xj, or the negative of that. I change the coefficient, switch the coefficients and change the sign on one of them.
Oh, okay.
Which is what we just, is what we're about to do for that problem. So with that last problem, I got my the coefficients to my unit tangent vector, switch them, and I changed the sign on one of them. But the only thing I haven't done to finish that problem is I haven't actually decided which one I'll change the sign on yet. So I'm going to go back and do that. But the third method is the long method, but the most kind of reliable in terms of a 3D space vector where you make use of this formula. And eventually you compute everything except n and then solve for it. So the acceleration vector will be r double prime, unit tangent vector you'll have found, and there's formulas for a sub t and a sub n.
Right, okay, I think I understand now.
Okay, so just to go back to that one that we were doing, so any questions about this before I move this screen on? So if I remember it right, n was 6 over the square root of t to the power 4 plus 36i plus t squared over the square root of t to the power 4 plus 36j, but maybe negative. Is that right? Yeah, no, one of them had t squared and one of them didn't. And so going back to the original problem, remember, r was ti plus 6 divided by tj. So that's the graph basically of y equals 6 divided by x, which we know to be a hyperbola. So that's the thing that's been described. Specifically, it would have that sense of direction as t increases. Notice t can't be 0 here, so we have a jump in that curve. But what this, and let me just write down t again. It's back in blue. T as we had it was t squared over square root t to the power 4 plus 36i. I think, was it minus 6 over, is that right? Yeah. Minus 6 over the square root of t to the power 4 plus 36j. So the question's asking me about when t is equal to 3. So let's just think about that situation. Well, r of 3, going back to the original thing, would be 3i plus 2j, right? So I'm basically at this point here. Here's t equals 3. The unit tangent vector at 3 will be t squared, so 9, divided by the square root of t to the power 4, so 81 plus 36, so that's 117i minus 6 over the same thing, square root 117j. Well, you can see that my unit tangent vector here is this. So it kind of makes sense that it's got a positive I coefficient and a negative j coefficient. And you can see that ratio of 3 to negative 2, so it's kind of got that negative 2/3 slope. So the question becomes, what's n? Well, notice that n is going to be either this or this. It's going to be normal to that. Is it going to point bottom left or top right? It's going to point top right in this case, because that's the direction the curve is curving, if you like. So in this case, this is the n I'm looking for. So I want both of them to be positive. So remember, n, we said switch them around and change the sign on 1. In this case, n will be 6 over square root 117i plus 9 over square root 117j. But notice, if I had instead picked this point over here, where you can see, notice the unit tangent vector will always be positive I, negative j, right? Every unit tangent vector anywhere on that curve points bottom right to some slope, sometimes steeply, sometimes shallowly. So my unit tangent vector is over here, but in this particular point over here, n would have been pointing bottom left. I would have wanted both of them to be negative on this side. So that's why I can't just write down n in terms of choosing between the plus or the minus sign, because some places on the curve I want the plus version, some places I want the minus version. All right, but as soon as they assign a t value, now you can say at that particular point, here's my answer for n definitively. And so this is the n they're looking for here. Does that make sense? But it does require you to know what the graph looks like. You know, notice the only way I was able to pick which n I wanted was by looking at the curve and seeing which direction it was going, right? I couldn't just look at the formula itself and make that decision. That the functions themselves didn't tell me that, only the visual of the graph told me which n to choose. If you go with the t prime divided by its magnitude, that will take care of it. That will actually give you a single answer that is the right direction, but it's a much more complicated process than it needs to be. Adding in the complication of looking at the curve still keeps the problem much simpler at a two-dimensional level doing it this way.
And we're going to have to graph to ourselves in the test, right?
It'll be something where you know what it looks like. Something like a parabola or a straight line. Or...
Can you walk through how you got the graph again, actually?
So any graph that's of the form y equals something divided by x is always a hyperbola.
Yeah, did you use the parametric?
Oh, sorry, I see what you're saying. I just looked at this. So basically x is t and y is 6 divided by t. So I eliminate t and say that means y is 6 divided by x. But usually parametrically, Not always, but usually x is t, and so in the other part where you see t, you just switch it out for x. Not always, especially if it's you might have sine t and cosine t involved or something, but
we don't need to know like exactly what the graph looks like.
No.
We need to know, like,
right, yeah, you don't have to like put in details of coordinates or anything. It's just knowing just enough to see curvature and which way to go. Okay, that makes sense? All right. Like I said, on the in-class, that's the kind of thing we might be looking at, a plane curve with only I and j components. The ijk stuff is a much longer process where I'm interested in you being able to do it, but I don't really care how fast you do it. So that I'd put that on a take home. Okay. All right, what else? Yes. Oh yes, you asked about that yesterday, didn't you, Olivia? Projectile motion. Right, do you have one in mind or just? Now again, oh, go on.
With that, like, there's those cases where we'll be given like the acceleration, right?
Yeah. Well, in a projectile motion, you're not really given acceleration. It just is always negative gj to start off with. That's what makes projectile motion. If there was any other acceleration, then there's something else, some other force being applied. But by definition, projectile motion always starts with that.
So we'll have to, like, just using that, we can go down to kind of R.
Right.
That's how we do it.
But so what you will be given, though, that will vary from question to question, is the initial position and the initial velocity. Now, being a, you know, there's two ways that they can do that. You could either say initial velocity or initial speed, whichever way they want to phrase it, and then give the thing. So you could say initial velocity has like a speed of say 20 miles an hour at an angle of say 40 degrees. That's one way of setting it up. And we developed our formula with V0 sine theta, V0 cosine theta, etc. But you are really going to need a calculator to make proper inroads into answering that question. The second possibility is, which isn't as practically useful, but does mean that a non-calculator test becomes more doable, is that you're just given the initial velocity V0 as a vector. So you could be given it as kind of, say, I plus 3j, which is, you know, I plus 3j is less easy to kind of visualize exactly what it means, because it implicitly tells you the angle and the speed, but you'd have to sort of think through it. Whereas, you know, if I say to you 20 miles an hour at 40 degrees, that's easily visualized. But the second one would make the math much more straightforward, because when you come to plug in V0, you've got an I component and a J component. So let's go ahead and do that. All right. So let's imagine that we've got this initial velocity of I plus 3j from an initial height. Now I'm just making this one up, so the kind of questions I might ask won't have nice integer solutions, but we can still illustrate the idea behind it. So the initial height, h, might be, let's say, 4 feet, something like that. And watch out for the units as well, because the units will determine what value you use for g as well. Don't forget, g is either 9.8 meters per second squared, or it's 32 feet per second squared. So if I give you the initial height as 4 feet, I'm basically telling you to use the 32 value for g. So if this is my question, taking away that, because those part 1 and part 2 aren't the same thing here. They're just examples of the kind of thing I might give. So let's imagine I give you this question. Projectile motion, an object hit with an initial velocity of I plus 3j. Which, like I say, if you know I plus 3j, you know, it was hit from a height of 4 feet here. So the initial velocity is that. Which means if you needed to work it out, you could work out that the initial speed here, well, it's the magnitude, so square root of 1 plus 9, so square root 10. And the angle, well, the tangent of the angle here will be 3 divided by 1, so it's whatever the inverse tangent of 3 is. So should you need to know the speed and angle, you could work it out. But given you don't have a calculator on this test, me giving it you as a vector makes your life easier, even though it might not be the most practically useful way of describing a initial velocity. So let's go ahead and do this one. So we've got A, in this case is negative 32j, which means I could integrate to find V. Well, I've got no I component originally, so if I integrate 0, I get a constant. And then for the j, well, if I integrate that, I'll get negative 32t plus a constant. So my velocity looks like that, but C1 and C2 I don't know until I consider the fact that the initial velocity, v of 0, which will be C1i plus C2j, the question gives me is I plus 3j. So this is what I was saying. If I told you instead speed and angle, then you'd need to be working out things like, you know, in previous example, 20 cosine 40 degrees and 20 sine 40 degrees to get your value of your constants, which with a calculator is fine, although there's still decimals. But here I'm basically just giving you C1 is 1 and C2 is 3. So now I know velocity. It's I plus 3 minus 32tj. Which means I can now work out R, because if I integrate again, I'll get R. Well, the I component right now is 1. So if I integrate that, I'll get T plus a constant. And the J component, 3 integrates to 3T minus 16T squared plus some constant. But again, I know R of 0 as well, because this thing starts at 4 feet above ground level. So R of 0, which is C3I plus C4J, is basically 4J, right? If it's 4 feet above, well, we might as well think about the object starting on the y-axis. So X is 0, the height, the y-coordinate is 4. So C3 is nothing. Although that's, to some extent, that's my choice, is to make C3 nothing. So we're measuring everything from the y-axis, which is logical. And C4 before. So I finally, after all that, have the position vector of the object. Right? This object is Ti plus, well, I'll write it out with a T. So minus 16T squared plus 3T plus 4J. That gives me the position of the object at any time t. And that's the bulk of the work for projectile motion, creating the position vector from the original setup. Does that make sense? But you'll be asked questions about it. So let's just think about what this means. So I'm going to go to the next screen. Can I get rid of this screen? Everyone happy with that? So I've got R of t, so write that back down, is ti plus negative 16t squared plus 3t plus 4j. Well, notice that tells me the path that the object travels, right? A bit like last time, that's parametric. So y here is minus 16x squared plus 3x plus 4. Now, not that you need to do this, but certainly if you had a calculator, you type that in, you'll see exactly what the path is. But that's a parabolic path with a negative leading coefficient, so it's an upside down parabola. And so if you graph this, well, I don't know exactly what it would look like, but I do know that it would pass through 4. It's got a y-intercept of 4 and then goes up, turns around, drops back down again. And things you can be asked about are things like, what's the maximum height? Or how far does the object travel? So let's imagine I asked for the range of the object, aka how far does it travel, how far has it gone when it lands, or whatever. So basically it's asking me, what's this? And so you just have to think to yourself, well, what condition is being satisfied at the point where the ball hits the ground?
Wouldn't that be y equals 0?
That's exactly what it would be, right? That's the y coordinate is 0. So to answer that question, I would solve where minus 16t squared plus 3t plus 4 equals 0. And this is what I mean, because I just made this question up, that's not going to have an integer solution. You know, you're going to need the quadratic formula. It won't factor. You need the quadratic formula. T will be minus 3 plus or minus the square root of 9b squared minus 4ac is plus 256 all over 2a is negative 32. So that's not a pretty number. But, you know, on the test, I'll make sure that it is. On the test, I'll make sure you got a quadratic equation that you can solve by factoring. But do notice there's two solutions here, but I'm only looking for one of them. How do I know which one to choose? The positive one, right? One of those is going to be negative, right? If I do negative 3 plus square root 265, that's a positive number, and then I divide by negative 32, that's going to give me a negative value, which, I mean, it has meaning. It's graphically, it's that y-intercept, sorry, that x-intercept over there, but in terms of our problem, it has no meaning at all, because there is no negative t. T equals 0 is the moment that you hit the baseball or throw the object or whatever it is. So what I would want for this is minus 3 minus the square root of 265 all divided by negative 32. That'll give me a positive number. That's the time when it hits the ground. How do I work out the range? Plug it into x, which in this case x actually is just t. So actually that would actually be the answer in this case as well. But once you've got your value of t, plug it into x, whatever x is, and that'll give you the distance traveled. We also talked in class, if it had asked instead for the maximum height, well, maximum height occurs when the vertical component of velocity is 0. So you go back to v rather than r, and check where the y component of velocity is 0. Again, that will be a time. Plug that back into your position to find the maximum height. So projectile motion question could simply say, here's the setup. One question could be, where is the object after 2 seconds? Which obviously that's easy enough. I just plug t equals 2 into that top expression, and there's my answer. So if the question had said, where's the object after 2 seconds? Well, it's 2I, and then I've got, well, I guess actually 2 seconds, this thing will be negative. This actually, the way I've set this up, this hits the ground very soon, doesn't it? So let's say after half a second, just to keep this meaningful. After half a second, this is at 1/2 I, and then the j component will be minus 16 times 1/4, so minus 4 plus 3/2 plus 4. So after half a second, it's traveled half a foot, so 6 inches horizontally, and 1.5 feet, 18 inches. Well, it's not travel, it is 18 inches above the ground level. This is a mess of a question numerically because of the way I kind of set it all going. But, this hits the ground very, very soon. Realistically, 3I plus 2J is almost nothing compared to gravity. So it's kind of gone and just like flopped on the ground. If I'd made the initial velocity bigger, it would have been a much more dramatic thing. But yeah, this is something like so yeah, 3 things I could ask about this are, where is the object after a certain number of seconds? Or what is the maximum height of the object? Or what is the maximum range of the object? I.e., well, I guess I could say, when does it hit the ground? Or how far has it traveled when it hits the ground? So there's a variety of things I can ask, but they all basically come down to the same concept. Regardless, you're going to need this expression, whatever I ask, and that's about 80% of the work, right? What I then ask will tell you specifically what to do with that, and there's a few different things I could do, but they'd all be coming out of the same setup. So, it's a good question because there's definitely, there's definitely going to be projectile motion on this thing. And then there were other questions that are very like this. They weren't projectile motion because I gave you some different kind of initial acceleration. But if you look back in your notes, can I get rid of this? Is everyone happy with this?
In this case, like the time it took to the ground would be the same as the distance. Is that right?
Yeah, because x is t, then yeah, it would be. But that's just coincidence for this. It was because my initial velocity was 1I that caused that to happen. If my initial velocity had been like 7I plus 6J or something, that would have changed that dynamic. But if you look back in your notes, you'll see other questions on that, where I tell you the initial acceleration might be like negative ti plus sine tj or something, and I tell you the initial velocity and the initial position. So I might tell you that v0 is 3I minus j, and r of 0 is 4I plus 8j or something like that. That's basically, from a math point of view, that's exactly the same question. I've given you a different acceleration. It's not as simple as just minus 32j anymore. But what you do is the same. You integrate a to get the velocity and sub in to find c1 and c2. And then you integrate again to find position and sub in to find c3 and c4. The only difference is that this one doesn't have the same physical meaning. Projectile motion has a very definite physical context. This is a more, this still is a physical context, but it doesn't have any I'd struggle to find a real world situation where something has this acceleration naturally. You know, that would have to be a very artificially created acceleration by choosing force. But from a calculus point of view, this question really is no different from the projectile motion question we just did. So you'll end up seeing that more than once on the test because we've looked at it in more than one context. So, and this does form a significant amount of the in-class part. You know, this plus curvature is you know, what we've done today plus curvature is really the bulk of it. Tangent vectors, normal vectors, and this process. There's a lot of mileage in that. So, okay, any last quick questions, Lee?
And since you said we won't have a factor on the test, we are more likely to get velocity as a vector.
Yeah.
Like
Yeah, I wouldn't give it you as, because the only thing I could then do is use unit circle angles, and it still ends up being, you know, you can't solve quadratics with things like square root 3 over 2 and stuff. So yeah, I'll give you velocity as a vector. Again, on the take home, I can make it more realistic and let you use your calculator. So, you know, that'll be a different story. All right, so I'll see you here Monday for the in-class, and the take-home so the take-home will be due Thursday, just for budgeting your time next week. You'll have 3 days to get that back to me. Hang on, I just missed that question there, Ashley. All right, yep, so are you still on track to be back in class with us Monday? All right, excellent. Then I'll see you then, and enjoy your weekend, guys. If you got any questions while you're studying, I'll do my best to get back to you as soon as I can.